Hopefully it says I'm going live. Hopefully it says I'm live. Hi all. I hope everybody is enjoying their Mother's Day. If you're in the United States, happy Mother's Day, and thank you so much for being with me. I know that Mother's Day isn't necessarily an easy time for people to meet. It just so happened with my finals for Millersville, that was kind of the only time I could come in and get something done for you this month. So thank you everybody for joining. I appreciate that. Hi Dave. Hi Lisa. Oh, good to see you. Hope it's not too late in Scotland. Art, hi, good to see you. Julian, great to see you guys. Thanks so much. Jerry, wonderful. Everybody be very nice to Jerry Ryan. He is one of our VIPs and also a moderator of this of the forum, the live chat. If you have questions, he's very knowledgeable and he can help you immensely. He can also, if you have questions that are not being answered by me and you desperately need them to be answered, ping him, because I do always perk up anytime I see him writing, and that your question will definitely be it will definitely be caught. Also, anybody who has my cell phone, I do have it on and ready. So if you need me to contact me for whatever reason, please feel free to do so. I will keep it on. Oh, wonderful. Mike Richardson is also here. He's also a VIP and a moderator of the forum. So please, if you have questions, talk to Mike as well. Either of those two are very knowledgeable and they can help you with pretty much anything, including getting a hold of me if I am not responsive in the chat. And if I'm not, it's just simply because there's lots of stuff going on. So I'll do my best to catch everybody though. Hello, everyone. And yes, happy Mother's Day if you are in the United States, and if you are have a mom, which I think most of us do, hey, give her a big hug and squeeze, because it's a great day for mothers. And I appreciate you all being here with me. And please, I beg forgiveness for any moms I'm taking your children away from you during this Sunday. Okay, so I have a lot of people to thank, and I'm going to get to it right this second. First of all, I want to thank my mini course patrons. Thank you all so much for, continuing this journey with me. We are almost completely through our space weather basics, essentially. Can you believe it's been almost, what has it been? Almost 2 years. And it's taken us that long just to get through the basics. We are now getting to the ground finally, and we're going to take a look at some of the indices that you use, that you may have been using for years, trying to understand space weather data and not quite sure which index to use or why and what it means. And we're finally going to put all of this together. And you'll see very shortly why you needed to have all of this stuff from the sun all the way down in through the atmosphere, down to the ground, where we can now put all of this together so that we can see why the indices respond the way they do, why the Earth responds the way it does. So you'll be very appreciative of the fact that you have, if you've taken all my other courses, that you have all of that information. And it's really all due to these folks right here who have been supporting me and helped steer the direction of the mini courses. So thank you all for being with me for so long. And then, of course, I would be remiss not to mention my steering committee and also some of my my one-on-one and Radiant Star patrons who have absolutely been supporting me above and beyond the level that I could, that I can even know how to be grateful for. I'm just absolutely in awe of all of these people, and then and also of everyone here who has been on my steering committee for so long and has helped me kind of steer the direction of this whole Patreon project, and gotten me to kind of get to where I am today, not just with the mini courses, but also with all of the outreach stuff that I do, and even getting into the Millersville University and teaching courses there as well. And we have lots of plans for the future, so that's coming. Also, one other thing you might notice is I do have down here, I hated to have to do this, but I have this now. The reason for this, and I'm not going to put this as a watermark on everything, please let's hope that the community doesn't force me to do this. The reason why is that I'm noticing more and more people are lifting the charts from these mini courses and thinking that they can teach them on their own. Please understand, when I teach these courses, I teach just the basics. I don't teach anyone enough space weather to be able to be an expert. And so you'll know enough to be able to make your way through the indices and make your way through the data and the information, but it's not enough to get you to be a teacher or an expert on your own. So please don't lift these charts off of YouTube and try to think that you can teach them, because you will get yourself in trouble. And I've already gotten complaints from the scientific community because people are trying to do that. And if I have to watermark these charts, it will just kill me inside. I don't want to have to do that. If you have a heliophysics degree in some discipline, great, that's wonderful. If you really want to teach these charts and you don't have a heliophysics degree, get one, then teach, okay? Because prior to that, you really are just going to do a disservice to yourself and the community. So please don't. So that's the only reason why this copyright is on here. Everybody who owns their own, the information that I present here, it's not all owned by me. I don't pretend to own any of it, to be totally honest. I have a little bit in there because I'll teach some of my material, but this heliophysics field is massive, right? So there's so many people that contribute to this field. So this copyright is just simply to indicate that the way I'm teaching the courses and the methodology is mine, but the content in the courses belongs to the original owners. It always has. So please just know what you're teaching. If you're going to try to teach, get a degree. Otherwise, you're just in trouble. All right, I'm going to get off my soapbox and stop talking so that we can get into the actual material of the classes. And thank you so much, guys, for joining me during this period. And I see lots of people saying hi even from places like the Netherlands and Morocco. Oh my goodness, good to see you. That's so fantastic. Thanks so much. Okay, so let's start. Now, hopefully those of you who have been learning from my stuff for quite some time, you recognize that, we've gone through a lot of material, right? The space weather regime from the sun to basically near Earth space, I call that regime 0, mainly because I hadn't thought of teaching in terms of regimes until I got to regime 1. I said, you know what, I need to call these regimes. But since I had already labeled these 1, 2, and 3, I said, well, let's just call this 0. So this is the one that goes from the sun. This is basically from the sun to near Earth space. That's what we called the first chef, right? Then we jumped, and that's all the space weather phenomena from the sun to up to the point where it almost starts getting into the near Earth space and gets all scrambled up in the Earth's magnetic system. Then we jump inside the Earth's magnetic system in 3 different regimes because they're also complicated. And we call this the second chef, right? So the sun is the first chef, the near Earth space is the second chef, and it takes those phenomena and scrambles them up, kind of like cracking an egg in a skillet, scrambling it up, and then it serves all the way through the near Earth system into the upper ionosphere and atmosphere, and then down on the ground, which is where we are now. This is where those scrambled eggs finally land on your plate and you have breakfast, right? This is where we're going to learn now what happens on the ground and how those scrambled eggs end up actually making sense and actually tasting good, right? It's tasty. Space weather is good food. I'm making me hungry. I haven't had breakfast yet. And then maybe we'll end up putting some of the picture together. It depends upon what you guys would like. But what we can do is afterwards, we can demonstrate how some of these indices work in actual storms and show, through demonstration, because a lot of times that's the easiest way people recognize and can internalize things. But we will not get through all of it today. I guarantee you that. This is just like all the other regimes, is going to be a multi-step process. So all of you who thought that you're going to learn all of the indices today, let me just strike that down right now. We'll get through some of them, but we're not going to get through all of them, because just like everything else, it's complicated, right? Okay, so the heart of the Earth's magnetic shield is a dipole field. You should recognize this slide. This is one that we're just going to do a little bit of a review, and I'm going to do it quite quickly because all of this is from courses that we've already had, right? This one, for example, if I get out of the way, and I probably should move my light here so that I don't know if I should move it here or here, because I want to be able to see the chat. This course here, or this diagram here, is one that you should recognize from the M series. This is talking about the Earth's magnetic field and how it's ordered. And you should also by now, if you have studied in that course, recognize where this diagram is wrong. And it's wrong right here. because all of these particular field lines don't map necessarily to exactly the same location. So this is one of the neat things about learning space weather, is that you can actually start seeing official diagrams and recognize where they don't work correctly, right? Because all these field lines shouldn't be mapping here. They all should be mapping to different locations on the Earth relative to where they are out in the Earth's magnetic system. But the heart of the Earth is essentially a dipole field, and it doesn't change all that much, but it is dynamic in the sense that it wiggles just a little bit. Okay, so we're recognizing this, remembering this from the way back when, from the way back when machine. We're also recognizing that the geographic pole and the Earth's magnetic pole are not in the same location. Okay, and that makes a big difference, because we have to turn about and think about things from a point of view of magnetic latitude as opposed to geographic latitude, right? Because it matters. Everything, once you get into the Earth's magnetic system, is ordered by the Earth's magnetic field, not by geography. Okay. Here's a better diagram. This is more like what we should be looking for. You notice that all these what we call L shells, right? If you remember the term L shells. If not, please go back to the M series and learn about the Earth's magnetic field. The L shells, as we know, which are mapped out and are numbered based on how far away from Earth, in Earth radii, how far away they are from the Earth, the center of the Earth. So here's 1 Earth radii, which is the surface of the Earth, and 1.5, that's L 1.5. Here's L of 2, here's L of 3, L of 4, L of 5. They're all defined in the equatorial plane, okay, of the Earth's magnetic system, right? And the reason for that is because that's as far out as they reach. As you follow the L of 5 shell, this L shell, back down to the Earth, it actually reaches the Earth. So obviously it's not 5 Earth radii out, it's actually at the surface of Earth here. So that's why we have to define them at the equator, because it's the furthest that particular shell reaches out. Also remember, why we call it a shell is because it actually isn't just this line, even though this is a field line. The field line actually is carving out a shell in the Earth's magnetic system. So this is my favorite thing, right? This is a slinky, right? If I flip this slinky around and make it like a toroid and turn it sideways, okay, this is what we're dealing with, okay? We're dealing with magnetic. So like here, if I can keep my slinky flat, right? Here is something that kind of looks like an L shell of, this way. Here, there's L shell of 1.5. Okay, got it? Right? And I flip it this way. Okay. So you can see it kind of, if you cover this, it comes like a shell. It's like a solid thing. So that's what we're dealing with here. And we're just kind of making a cut right through the middle of it to see them as lines as opposed to shells. But that has a lot to do with how how the particles move in and around this stuff. Remember, we talked about 3 different types of adiabatic invariance, 3 different types of motion that particles go through. You have gyro motion, which is the spinning around, the helical motion around the magnetic field lines themselves that jail these particles and prevent them from moving freely. And then we have bounce motion, where they bounce from one pole to the next and back again. So they're gyrating, they're bouncing, and then they drift. And depending upon their charge, they'll drift either to the dawn side or to the dusk side, right? Clockwise or counterclockwise, depending upon how you're looking at the whole system. And that is a really good egg beater. To be honest, I mean, it's really kind of like an egg beater that you just stick these little mixing things in, just stir up everything. And because of that, once big solar phenomena enter the Earth's magnetic system, they get mixed up, right? It no longer looks like what you'd think. A solar impact, from let's say a coronal mass ejection, right? A big solar storm, when it impacts the Earth's magnetic field, it does not do what you think it does. It does not slam into the front of it and enter straight in, right? It actually takes these L shells and it peels them back, peels them from the day side to the night side, and it actually changes and reconfigures things. And then once the particles get in to the system, and that's complicated in of itself. Once again, that M class series, course series, tells you all about it. Once you get into the Earth's magnetic system, then the Earth's magnetic field takes over, and then it begins to scramble everything. Okay, but the neat thing about this system is that, as you can see, the L shells are mapping to certain latitudes, right? So when we go to a map down here, Recall this, guys? Do you remember this? You have the L shells mapping to certain latitudes on the planet. Okay, that is super important, right? And this is magnetic latitude. That's why you see the dip. It's not geographic latitude, right? So the dip is up because the Earth's magnetic field is tilted relative to the geographic field. So you don't have just a straight line where you'd have the equator. The magnetic equator would come kind of along this line and then dip down. Oop, not so far. Dip down here and then back up. Okay, across the Earth's magnetic system, or across the Earth's geographic system. So they're not completely aligned. But what is nice is that as you go higher in latitude, you go higher in L shell. So in other words, as you go higher in latitude and up to the poles, you go out to the edge of the Earth's magnetic system, the part that's actually interacting with the solar wind, right? And obviously that part's going to be a bit more disturbed. And once you get into the inner part of the system, especially down in here, that heart of the Earth's magnetic system is disturbed less and less and less. Okay, and it gets a bit more quiet, right? Because it's being protected to a great degree. And it's also got current systems that are very well established. And they're doing things, as you will see, that cause a certain kind of dynamic that allows you to measure the certain aspects of how disturbed the Earth's magnetic system is. And depending upon which current system you're looking at, right, that different current systems are at different locations in the Earth's magnetic system, well, you can then look at different indices and different stations, different places on the Earth's, on the surface of the Earth, and expect to see different types of disturbances, right? If you're looking for something that's out here, you're going to look at on the ground, well, you're going to look somewhere in this area. If you want to look for something down in here, well, you're going to be down over here looking in this area. See how that's working? So if you're very careful, and this is how scientists became very savvy, is that if you're very careful about setting up your instruments, okay, in this case, magnetometers, and looking for disturbances in those magnetometers, the way the Earth's magnetic field is wiggling or changing. If you're very careful about how you set that up, well, then you might actually be able to isolate different regions inside this magnetic system. And that's exactly what these indices do. And we're going to go into that. But a little bit more of a review. Okay, I'm trying to go through this reasonably quickly, but I want to make sure that you guys have all this in your mind, because it will help you understand how the systems work and what the limitations of these current systems and what the limitations of these indices are, okay? If you're wondering why I'm giving a review. All right, so hopefully you're sick of this diagram. But once again, we're going to go over it, okay, very quickly. But we're just going to talk about a few things. We're going to highlight a few things in here because these are the things I'm going to need you to pay attention to. So the first is the ring current. Okay, if you recall, here's the Earth's magnetic system. Once again, the sun is coming in from this side, right? Here is basically the edge of the Earth's magnetic system. This is what we call the magnetopause, right? Here is the Earth itself, and this is kind of a meridional cut. You cut vertically through here, you cut horizontally through here, right? So this is the Earth's equator, and then here is the Earth's North Pole. The South Pole is hidden underneath. Okay, so the ring current is that current system that goes around the Earth in about this location. We'll talk a little bit more about this. This is in about L of 4, okay, ish, give or take an ish. Maybe a little bit inside it. And inside, yeah, I mean, we even have it located at L of 3 to 5. It's a westward going current, okay? And what happens is that when you have this westward going current, remember with Maxwell's equations, and I'm not going to go into those, so don't worry. But what happens is that when you have a current, something that is changing, an electric field is changing in time. So this is a current flowing. When you have that changing in time, that will induce a magnetic field. Okay, and vice versa. If you have a changing magnetic field, that induces an electric field and therefore a current, most of the time. But the thing is, with the ring current, because it's a westward current, what it does is that it serves to increase the southward pointing magnetic field. But the Earth's magnetic field is actually, I got to be careful how I say this. It's going to it's going to, let me just say it this way, it's going to induce a magnetic field strength that is going to serve to reduce the main magnetic field strength in the Earth's magnetic system, which then reduces the field strength that is seen on the ground. Okay, so you have a field strength of the Earth's magnetic system, that is the magnetic moment, and the moment points in a particular direction. And that direction then is when you add this current system, when it gets enhanced, this current system will serve to induce a field, a magnetic field locally that is that weakens the overall field. Okay, how it does that is that it's inducing a magnetic field locally that is the opposite direction of the Earth's magnetic field. So on the ground, locally, in and around where you can see this, meaning, and what I mean by locally now is L shell, okay, because we're looking at L shell of 3 to 5. So on the ground in that local area, it will then depress what is seen as the Earth's magnetic field. Okay, and we'll get into a current system or an index that actually measures that. We'll talk about that in a bit. Okay, and I'm not going to go too much into the details of it, but it's this current system, if you recall from our M series, this is the most it is the largest current, the biggest, and contains the most energy of all the current systems, and is the one that's really, in a sense, I don't want to say the inertia, but it's the energy inertia in that sense. It's the one that really takes a long time to get going. But once you get going, it's hard, it takes a long time to stop, to kind of melt, calm back down. So this is the current system that we use to determine whether or not we have a really strong geomagnetic storm. So in other words, a really big solar storm that hits Earth, causing disturbance over a long period of time, can really ramp this system up. Okay, but it takes a little while. And once it ramps up, right, or if the storm is strong and sustained, this current system will really start intensifying. And once it intensifies, we know we're in a geomagnetic storm. Not all storms do that. We have things like substorms. They don't intensify this because they don't really last. They don't have the oomph. they don't have the staying power. So that's why when we look at the ring current, we look at the ring current from a very particular point of view, and that is from the point of view of a big storm, okay, a sustained storm, or otherwise known as a geomagnetic storm, okay, not a substorm. They're not the same thing. We also have a plasmasphere, right? And we'll talk a little bit about the plasmasphere. And this is only to kind of like give you an idea of the motion of things, or really where our atmosphere, kind of the upward extension of our atmosphere. Okay, it is considered an extension of the ionosphere. It does co-rotate with Earth, so it's moving, and there are plumes and things that cause that we talked about in the M series and also in the I series that cause leakage from this region out to the edge of the Earth's magnetic system. It's definitely cold and dense, but it's the most massive, obviously, because it's part of our atmosphere. Even the plasmasphere is more dense than the ring current, even though the ring current contains most of the energy. The plasmasphere contains most of the mass, but it's cold, so it doesn't really have as much energy. But that whole region, the plasmasphere and the ionosphere, really cause certain types of currents to unfold. And we actually, to a great degree, have to subtract out some of that stuff. We'll talk about that in a minute. Now, the plasmasphere does have a much more sharp boundary, but that boundary moves in and out, and it's out basically at the edge of the ring current. Okay, it extends outward a bit, but it can shrink inside. But we do have a really strong boundary. So if you look at L value, remember this is our L shell again, you can see where that plasmasphere, this is density moving up on this side, you can see that plasmasphere is actually quite high, and then whoosh, it just cuts off. As a matter of fact, we can image that big cutoff because we can see where air glow stops. It's really kind of neat. And I'll show you, that might be coming up here in a second. Yes, it is. So here's a variation of plasma pause location over the course of time. This is to remind you that things do move in and out. So normally you'd have a plasma pause during quiet conditions. You'd have a plasma pause that would come out to here, and then, or not quiet conditions, just normal conditions. And then during a storm, okay, you can actually have it compressed or actually leak out or actually have it be gone. So the plasma pause can actually really get squished and dynamically move in and out. And you can see again, here's some some images of the plasma pause location during storm periods, and also you can see it that it's being imaged by air glow. And so we're looking down, sorry, let me explain this. We're looking down at the North Pole. Here's the day side of Earth. Here's the night side of Earth. So the solar wind is coming in from this side, and it's kind of blowing, as you can see, blowing back this way. But you can see when you get impacts, how much that plasma pause location can shrink in. Okay, and here is a model representation of where that boundary is. Okay, where you can see where that big strong cutoff is. I mean, that is a very sharp boundary. So it's inside, for the most part, inside of the ring current. Okay, so this kind of this part of our magnetic system, when we look at indices on the ground, we're going to be looking at indices. Well, no, I shouldn't say that. I got to be very careful. Because this is co-rotating with the ionosphere, so it makes a little bit of a difference. But when we're looking at let me talk about it from this point of view. When we're looking at indices, we're looking for the ring current. We're not going to be looking too much inside of L of 3, okay? Because we're going to be that gets so much into the plasmasphere. We got to be a little bit careful there. We don't want to get too low. But we do. But you'll see that we have this range of magnetometer stations that we look at for very specific reasons. And the reasons are because we have these really very, I don't want to say jailed, but they are to a great degree jailed boundaries that we try to keep isolated. And the point of me showing you this and showing you how these boundaries change is to show you that despite our best attempts, it's not so easy. Okay, so despite the fact that you'll see that we have magnetometer stations at very specific L shells, there is some overlap. There is no way to completely isolate this kind of thing. Okay, and so this type of bouncy, squishy, springy motion that is due to not just having an atmosphere that kind of billows in and out, but having a magnetic system that can be easily compressed and also expand, means that we will always have a little bit of trouble trying to look at things on the ground and isolate things exactly. Okay, there's always going to be some level of motion there. But hopefully this is enough of a reminder to kind of show you that there are ways. It's not a completely hopeless cause. There are ways that we can isolate it to some degree. Now, let's talk a bit about the radiation belts. Okay, so here's another big thing. Remember, we talked about these back in the M series, that these were some of the main populations of particles. And the radiation belts now, these are the ones that are the most energetic. Granted, the radiation belts are also the ones that are the least the least dense. Okay, but they have the particles in it that really take out satellites. I should be careful how I say that. That are a threat to the health and safety of satellites in various orbits. Now, the proton belt, the inner belt, or also called the inner zone, is really co-located with the plasmasphere. It's pretty close to being inside, or I mean, almost inside the ring current. Okay, it's very low. And remember, it also is the reason why we have the South Atlantic anomaly, because of the way the Earth's magnetic system tilts. You have part of that inner zone that actually pokes into, dips into low altitudes down near Brazil, right now, down near South America. So we have the South Atlantic anomaly, but it's really just the inner edge of the inner zone. And very high energies, right? These are the ones that cause single event effects and stuff like that. But it's really not one that contributes all that much to, to the current systems. Okay, it's just too tenuous. And here's a distribution and this is using the AP8 model, and I won't go into this too much. I'm sure Paul O'Brien will be very grateful for that. But we have, again, L shell, as you can see up here. You can see where the heart of it is. That's where all the red is. Okay, from basically L of 2 to 3. Okay, so we're inside, even in and around the plasmasphere. And you can see that the energies can get up to very high energies. Here's 50 MeV or so. And these are heavies. These are protons. And there's even other particles that are from anomalous cosmic rays and from craned processes. So you can actually get really high energy and heavy particles in here, not just protons. But the inner zone, it's not something that we usually look at as contributing to any of the current systems, or of course any of the indices that we see. So please don't get that confused. Now we also can look at the outer zone. Okay, sometimes just called the trapped particles, but it's oftentimes called the outer zone. This is the one that is electron heavy. Okay, and there are, and granted, there are electrons in the inner zone as well. They're showing the inner zone. Here is the outer zone. Okay, and as you can see the shell. See how this big green turtle shell? Right. This is over multiple L shells actually, and it's kind of gets filled in. And remember, the particles get filled in. The reason why is because of those 3 adiabatic invariants, right? You always have those little mixers going. So you have the gyration around the magnetic field lines. You have the bounce motion that makes them bounce from north to south and south to north, back and forth, and then they drift all the way around. So it fills this whole area. Okay, it's constantly being mixed, and this is due to the Earth's magnetic system. We do, even though we have an inner and outer zone that have electrons, remember the inner zone is mainly protons, the outer zone is almost solely electrons. And we've talked about the slot region. It doesn't always exist. You can see the slot region here. It gets filled in all the time, as you can imagine, because we have it mixing all the time. And there's always transient particles that come in here. But you can see for electrons, again, here's the energy, and here's the L shell. You can see there's electrons pretty much everywhere, okay? And that's the lower energy stuff. The higher energy stuff, you can see has the peak in the inner zone. That's this peak here, right? You get a little depletion, a little bit, not much. It doesn't last. People can't fly in the slot. I mean, people always, there's always the missions that think they can fly in the slot, but you can't. And then you get a peak out here. See where it kind of goes up again? This is a little bit of a peak right here. Doesn't look like it's so in the high energy stuff. The high energy stuff peaks a little bit closer in according to this model, the AE8 minimum showing solar minimum as opposed to solar maximum. AE8 is just aerospace electron, and it's the 8th version of the model. So don't worry about that. I mean, it's my old alma mater, so to speak. And so you've got the distribution here where you're peaking in and around L of 5. Okay, that's right. Remember, Earth geosynchronous orbit is 6.6, which is around here somewhere. So you're literally grazing the outer edge of the outer zone when you're in geosynchronous orbit. And so you're dealing with a lot of really high energy fluxes from these particles here. But the reason why I'm showing you this is because the outer zone changes dramatically. This is SAMPEX data from 1992, all the way to 2010. SAMPEX was a fantastic mission. I am sad that it's gone. So you can see that it actually changed. This is a horrible plot of sunspot number, but okay. You can see that it lasted for far more than a solar cycle. Here's one full solar cycle going up to a peak and then down and then almost up to another full peak. We had a sunspot maximum back in 1990, essentially. So almost 2 solar cycles. And here is the outer zone. You can see where the red is showing the intensity, so the most intense parts of it, from L of 2 out to L of 7, right? Here again is geosynchronous right here. See out at the edge of this zone here. The heart of it is sitting around L of 4, but look how dramatically different. Look at even the inner side of it, how much it goes up and down in L shell, okay? The Earth's magnetic system breathes. And what that means is that you're dealing with current systems that are not always in the same location, right? They're moving in and out a little bit. Not a lot, not a horrible amount. I mean, L of 3 to L of 5, that's not too bad, but they are moving. I mean, even the inner zone, as you're getting to the outer edge of the inner zone, you're getting down into very low L shells sometimes. And granted, if you're savvy enough, you'll recognize that these are solar energetic particle events being shot in from the outside, and they can penetrate quite deeply, clear down to almost L of 2, or maybe down to L of 2, if you believe that. But nonetheless, for the most part, the very inner part of the Earth's magnetic system, where the plasmasphere is, that's pretty well shielded. Okay, so you don't get a lot of solar energetic particle events from, or any particle events from the sun, just straight penetrating all the way down to our upper atmosphere. They get trapped, or they get caught, and they get caught in these different regimes, and it stirs up these current systems and enhances them and changes them. And we can, to some degree, start isolating what L shells can show us what parts of these what parts of the distribution, what parts of these particle populations we can look at. Okay, hopefully that helps you understand a little bit. So if I just kind of summarize some of these current systems really quickly, okay, hopefully again you should be very tired of this kind of diagram. We have a magnetopause current, right, which is mimicked by the tail current. We'll talk a little bit more about the tail current in a minute, because there's a few more considerations I want you to have. But we also have one of the main ones, which is the ring current, right? This is the one that goes westward around, all the way around and around and around. Okay, it's co-located with the outer zone to a great degree, right? The outer radiation belt. But the difference is the ring current is much lower in energy. Okay, it contains all the. Now I've got to be careful because it'll confuse you. The particles themselves are lower energy, but there's so much more of them than you have in the outer radiation belts that the ring current is where the energy storage of the Earth's magnetic system is. It's almost like an inductor, if you're familiar with it. You can actually store energy in this system, and when you store that energy, it actually depresses the Earth's magnetic field. It's very interesting how it works. Okay, but it's co-located essentially with the outer zone to a great degree. At least the inner part of it is. Inner part of the outer zone is. And then on top of that, we have the field-aligned current systems. Remember these field-aligned current systems? We have ways of measuring those, and I'll talk a little bit more about those in a sec. But notice the difference. They're at very high L shell, right? Because when we talk about region 1 currents, which are the blue, and region 2 currents, which are the red, they're sitting here at the very edge of our Earth's magnetic system, right? They're at the edge where you get the solar wind impinging. So they're going to be very disturbed very quickly, right? They're going to show a lot of more disturbance than, let's say, the ring current would, which is closer to the heart, right? So really, we're going to expect to see during different types of disturbances, different types of space weather events, we're going to expect to see indices that are associated with this region to be very different than indices that might be associated with the ring current. Right? And now get ready, because the tail current that you see both here as it's closing over the magnetopause and down here as it's cutting through the current sheet, the plasma sheet here, okay, these currents also affect Earth, but it's going to be very asymmetric, which we'll talk about in just a second, because you have a current sheet in the tail of the Earth's magnetic system, but you don't have it here, right? I mean, you have the closing current from the magnetopause, but that's not quite the same thing as having this big long tail, right? So you're going to have differences, okay? And here's another version of it when you're looking at the Earth from the tail. Okay, these are, again, pictures. This is all still review. You're looking at the tail current. This is in the plasma sheet. Okay, you have this massive tail current in the back. You don't have it in the front side of Earth. Okay, like I said, we're looking at Earth from basically midnight. Okay, and parts of that current can get disrupted. We call the substorm current wedge. We won't talk too much about that, other than to talk a little bit about what substorms are. But that tail current, okay, will cause changes, right? Just very similar to what a ring current does. It causes depressions in the field. Well, if you imagine you have even a bigger tail current out here, well, that might depress some stuff on the night side, right? But maybe not so much on the day side. So you have an asymmetry, right? So we have to deal with that, okay? But we also have stuff going on the day side that causes changes, right? Because on the day side, you have sunlight. Oh my goodness, now sunlight causes asymmetries because you don't have sunlight back here. So how does that affect current systems? Well, got it? So things get complicated, Oh, and here's, speaking of, here's the slide. Here's the slide I was going to show. So when you have a tail current, right, this is, believe it or not, and I talked about this back in the M series, you have a tail current that goes in the plasma sheet. So like here, so in other words, here's Earth kind of just sitting as a ball right here, okay? And the Earth's magnetic system is this big cone, right? Here's the front of it out here. And on either side, it goes like this into the tail current, okay? But if you cut through that like that, you're going to see this kind of system. That's very similar to like an Earth system with Coriolis forces, right? You're going to see two hemispheres that meet in the middle with the current going the same direction, and then they diverge. And they come back and they meet in the middle and then they diverge again. Okay? This system, as you're looking at it from the sun, as if you were the sun. Okay? This is dawn over here. This is dusk over here. So you have a current going across the equatorial region from dawn to dusk, and then it closes on what we call the magnetopause, right? Closes at the top of the thing. And you're seeing another version of it here. Here's Earth, and you're seeing this direction here, and it comes and closes. And what that does, okay, is it ends up creating a field at Earth, okay, that actually reduces the horizontal component on the surface of the Earth. And we'll talk more about what the horizontal component is. But the effect is stronger on the night side of Earth because the tail current is on the night side. So it changes and creates an asymmetry in the Earth's magnetic field, and you know, at the surface in these indices. And that's one of the reasons why you have stronger effects on the night side during geomagnetic storms. Okay, it's not just that you get particles shot up from the tail. It's not just that you get aurora that's stronger on the night side. You have a tail current to deal with. Okay, and it causes more geomagnetic disturbances there. Well, what about the poles? Well, remember the aurora? Remember how we have region 1 and region 2 mapping in? Again, this is just review, guys. Region 1 and region 2 mapping in from the edge of the Earth's magnetic system, mapping in, going across the poles and coming out, right? And you have region 2 that ends up mapping, coming in and moving up to region 1 and going out. Do you remember all this coupling, right? And you have part of it from region 2 kind of coming in and creating part of that tail current, part of that partial ring current that comes in. And on top of that, not to get too crazy, but if you recall from our last class and the class before that, we were talked about the Pedersen and the Hall currents, right? How the Pedersen currents are parallel to the magnetic field, and the Hall currents are perpendicular, right? So they create these vorticities. Remember all this? Okay, all of this creates complications, right? All of these things can complicate how the current systems are measured on the ground and create higher disturbances, higher level disturbances at higher latitudes. Now, on top of that, because of the way the sun comes in, it also drives currents because it's ionizing. It drives currents in on the day side of Earth. Okay, and we have convection patterns and currents here. We call these the solar quiet, and we'll talk about them. They're more like tides. Okay, and we have them going once again in the north in one direction, in the south they'll go another direction. Okay, so all of these things cause asymmetries on the day side. So realize that we've got so much going on that even though I'm going to show you all of these variations, and I'm going to show you these current systems, and I'm going to show you these indices, know that, first of all, we have to back out some of this stuff. Okay, we don't back out everything, because some of the stuff we would back out, like with the tail current, for instance, we want to know what's going on there. But for instance, the solar quiet, which I think I'll get into in a minute, we have to back out these other variations, because otherwise they could swamp some of the smaller deviations that we want to study from what's, from the disturbances that are happening at, let's say, higher L shell, right, out at the edge of the Earth's magnetic system. All right. And I think that might be the end of my little review. Hold on, I'm checking to see. Did somebody contact me? Okay, good. I'm all right. I think I'm all right. Hold on. Yeah, okay. All right, so before, let's see. Yeah, so I'm going to get into an introduction into the current systems. Now, before I do that, are there any questions? I know I went through this review reasonably quickly, but are there any questions on this? Everybody loves a slinky. Yeah. Playing catch up today. Yeah, well, definitely. There's one thing I want to make sure. And Julian, let's see, what did you ask? Moderators and regimes 3, troposphere plus ground. Regarding the troposphere, that's something I might get into a little bit. Probably not today, but I did mention it a little bit when we were talking in my very last class. I do believe I still have to get they're labeled the I series. I don't think I have them indexed as of yet in the mini courses on YouTube. I think I've been remiss in indexing them, but you can find them when you look in my past videos. Look for anything that says I1, I2, I3. That means ionosphere 1, 2, and 3. And in, I believe, the third of that series, which is the class I taught back in February, I think, that class went into some of the tropospheric effects. And so we talked a little bit, not that much about sporadic E or anything, but we talked about the, really at the time, I believe we were talking about the volcano. Remember the volcano that occurred? So we talked a little bit about how the neutral atmosphere ends up impinging upon the ionosphere and causing things like trans-ionospheric disturbances and waves and things like that. And I showed some examples of that, as well as a really good paper for you to read if you're so inclined to read geophysical papers, because it really talked about explosive events in the ionosphere and what happens when you have stuff from the ground propagating up and causing issues, and how that can actually affect how terrestrial weather can actually affect space weather, at least some of the things that we considered, we typically consider to be space weather only, like the ionosphere, the charged atmosphere. So hopefully you guys remember a lot of that stuff. If you don't, if this review seemed like completely alien to you, absolutely go back and look at the M series and look at the I series. The M series will focus on the big current systems that I was talking about: the ring current, the plasmasphere, the ring current, the plasmasphere, and the radiation belts. I will talk about those and how they kind of fit into the large scheme of things. I also go into L shell. And if you're interested more in the auroral stuff, because I went over the aurora stuff really quickly because I really didn't want to dive back into that. But if you want to look more at the auroral stuff and even get a hint at one of the indices we're going to cover today, which is the AE index, go back and take a look at the I series. And we go into that in great detail, because we talk about how the Earth's magnetic system and those L shells are kind of torn and reconfigured, and then how particles end up being shoved into the ionosphere using the physical and the mechanisms that we learn a little bit about in the M series. So hopefully that gives you an idea of where to look if you're kind of struggling with some of the review concepts I've just given you. Thank you for understanding this. Hi, hello. I see people saying hi to me. Yes, regime 3 is the ground, right? So we're just about to start getting into that. I just wanted to make sure that you have all of that information to know that I will be referring to that stuff. And if you don't have a good foothold in that, those are the areas that you're going to need to review. Yeah, the troposphere will be in regime 2. And we'll probably go more into it. I've had a few other questions about sporadic E and how do we look at that layer and how does that fit in. So I think what I'll be doing, probably not over this course, because I'm still going to be trying to get through the indices by the end of this course. But we will start getting into some of the more subtle details. And I might even pull up a few papers of some people that I think are doing some really interesting research in terms of that coupling, the ionospheric terrestrial, neutral atmosphere coupling, and where things might be going, because it's going to be very interesting. Let's see. Wait, what? Thank you. I wanted to know if troposphere is in regime 2. Right. Troposphere has its role to play in RF and radio frequency propagation. Yeah, that's a hard one. I mean, again, when we talk about the tropospheric propagation to do with troposphere, we start getting into how waveguides are formed and things like tropospheric ducting, and we get into the sporadic E layers and how they are affected by tropospheric weather patterns. Jim Bacon is a fantastic resource to look at from that perspective. He's been a terrestrial weather forecaster for so long that he understands terrestrial weather far better than I do, obviously. Um, and he has been looking at how to predict what the sporadic E layers, what basically the E layer of the ionosphere is going to be doing based on terrestrial weather. And he's had an immense amount of success with that. So, I mean, he's one of several that do it, but he's one that actually puts out his forecasts on PropQuest. I believe that's it, propquestco.uk. Anybody remember the actual website? But it's fantastic resource because he's, from what I've been told, he's far more spot on than not. And we might go into a class on that where I talk a bit more specifically about radio propagation and maybe reading ionosons and what skip distance is and how do you deal with MUF and all of that nomenclature. It really depends upon what the mini course patrons decide, if they're really interested in me focusing so tightly on radio propagation. What we might do, though, is we might also include in a class like that, we might include auroral propagation and maybe discuss how to use auroral propagation to help discover where aurora might be. Because I do believe, remember, radio propagation, radio frequencies can bend and see over the horizon a bit. And so you may not be able to see the aurora, but if you can hear auroral propagation, it's around. It's within a certain distance or something like that. And we might be able to talk about how radio frequency sounding might actually help aurora chasers find the aurora. It'd be pretty cool if we could harness that, and that way we could get more aurora chasers become radio operators, and maybe vice versa, and get the two the two different families of space weather stakeholders to cross-pollinate a bit more than they do. I think it'd be really neat. Anyway, that's for another class. But you guys can tell me what you think about that. Oh, good repetition, also new views. Oh, that's excellent. Good. Yeah, Jürgen, that's one of the things I try to do oftentimes is I try desperately to repeat. I know it seems kind of silly for me to do that, but that is one of the best ways to learn, is to have repetition, and concepts that may have sunk in to some degree end up sinking in more. And I want to be able to give you that and give you stuff that's repeatable so that you can hear maybe the same thing being explained, in different ways, maybe in different contexts, so that you just get a bit more of a well-rounded understanding of what it is. So thank you for letting me know that that's good. Okay, what's a good text for an intro on this material? Sadly, the only textbooks I know, even a couple undergrad textbooks, are almost a graduate level, and they're not really, they're because they're all math based, and so they end up going far more into the academia and the mechanism, the physical mechanisms, rather than going into stuff that is real world, usefulness for you. And so sadly, I've been asked to write a textbook on this, and I think I'm going to have to, because I keep searching for something that is going to be useful for people who let's say are radio amateurs, or people who want to understand this from a more conceptual point of view, and I just can't find one. I just can't find one, sadly. So, I mean, I could recommend the Dolores Knipp book. I could recommend, half a dozen different articles, and even I could even recommend the first year graduate text written by Russell and Kivelson and Russell, or even the Russell and Strangeway texts. But they're graduate level, and they're going to have a lot of math in them right away. And even the Dolores Knipp book, that's an undergraduate level, it's still, when I looked at it, it's got a lot of, it's expecting upper division undergraduate level E&M courses. So, if you're ready for that, then ping me again, and I can talk about it a bit more, but maybe in the Q&A afterwards. But yeah, outside of that, you guys just have to keep shaking me and say, please write a textbook, and eventually I will. So, which mini courses should you start with? If you're talking about for the second chef, start with the M series. If you're talking from the beginning, from space weather basics, and you want to know what, for instance, a coronal mass ejection is, right, a big solar storm, and the difference between that and, let's say, a solar flare or a radiation storm, then you need to start at the very beginning, which is the C courses. Those have absolutely no prerequisites. But if you look at the list and the series of mini courses I have on YouTube, every single one of them, if you look in the course descriptions or the series descriptions, you will see what prerequisites, and it'll say prerequisite C series or prerequisite C and P series or something like that. So you'll know, and there's an actual direction to follow. And I will post what that direction is. I promise. I promised people I will post it on my website, and I just have not had a chance to because I've been teaching too much this semester. But that is high on my list of things to do. So eventually I will have that on my website saying, go here, and then go here, and then go here, so that you'll see kind of what is the if it's not clear on YouTube, which direction to go in my mini course series. You'll see, I'll spell it out for you on my website. But you can see there in the description of each of the mini series, my mini course series, you will see what the prerequisites are. So you'll know which one. And the C course series is the only one that has no prerequisites, because that's really where it all starts, and it's where space weather kind of started, really, to be honest, is our observation of coronal mass ejections. Pretty neat, to be totally honest. That's really where all the instrumentation started. Okay. Oh, good, Lisa, you're taking a ham radio course this summer. Very savvy. I would love to see more Aurora people get ham radio licenses, and then use their expertise to be able to listen for auroral propagation and know that's, especially with a directional antenna, and maybe be able to chase down where aurora is that's over the horizon. And have success with that. That would be just so awesome. I think that's the next. That's where the aurora standouts are going to be. They're going to be the ones that don't have to see aurora to know where it is. That's going to be really cool. So I think the two communities really can help each other. Yeah, I'm not going to, Mark, it's great that you say Ben Davidson's books is excellent, but just like I said in the beginning of this course, I cannot recommend, if you are not a heliophysicist and don't have a degree in this, you will know enough to be dangerous, but not enough to be right. And I think you can be very, you might do a disservice when it comes to the details, because the devil is always in the details. And I've urged Davidson to get a degree. He has enough to probably do quite well. But it would give him, if he would actually take the time to get a degree, he would actually see the areas where he's not quite correct, and be able to correct those things, and then write a better book, to be honest. So that's what I'm waiting. I'm waiting for him to wake up to the fact that he really knows enough to get a degree, and he should do it. He should just do it, so that he can ensure that he gets it all right, and doesn't accidentally teach things that are incorrect. There's other people out there that are doing similar stuff that bothers me, because they're not helping. They're actually just making things harder for those of us who are teaching the correct stuff. Okay, good. Excellent. I will, Joanne. I will. I promise. I promise. I will write. I will write a textbook. I will. I promise. Okay. All right, guys. Yeah, good. Yes, Lost in Space. Get people to get their tickets, their radio licenses. It'd be awesome. Okay. So, oh, good. People are having fun with FT8. Excellent. Okay. So let me get into this since it seems like I've answered enough of the questions, and it sounds like a lot of people have had enough review, and it wasn't too outlandish for you. I'm glad, because that was my big fear is, oh no, what if everybody's forgotten everything I taught them? It's a lot to keep inside your head. Okay, so let's step into the current systems. Ready? Whew, here we go. Okay. So we do have we have the nice thing, and I've talked about it so many times, I probably don't need to say this anymore, but uh, the nice thing is that when we have these current systems in the Earth's magnetic system, these current systems will also do wonderful things in that they will cause magnetic fields to wiggle. Okay. And there's we also have all their other processes that are occurring in the Earth's magnetic system that generate waves, which will also cause the magnetic field to wiggle. And as these things wiggle, as the magnetic field lines wiggle, and and remember, because of the way the Earth's magnetic system is shaped, all of those magnetic field lines end up coming and anchoring themselves inside the Earth's core, right? Because that's where the Earth's magnetic dynamo is. So in order to get those field lines down into the core, they actually have to penetrate into the ground, right? Well, that helps us induce variations in the ground, both currents, electric potentials, electric currents. Right? The electric potentials allow electric currents to flow, and also magnetic field perturbations. Okay, so we can measure all of these things just by staying on the ground. We don't have to go out into space. That's what's one of the wonderful things. And as a matter of fact, that's one of the first ways we started understanding that there was something such as space weather. Was that because we weren't able to get out into space, but we were able to grab magnetometers, and measure the magnetic fields, just the same magnetic field that we measure with a compass on the ground. We were able to measure how those changes occurred. And the changes are, as we learned by sticking magnetometer stations in various places on the planet, we started seeing that there were systematic variations in these magnetometer changes, right? We'd see certain things wiggle a certain way, and certain things wiggle a little bit more in certain areas, and then certain things would wiggle in time a certain way. So like you'd get a wiggle here at this station, and then a little bit later you get a wiggle at this station, which is at a different local time. So you'd see things propagate both in time and spatially, from high latitude to low latitude and vice versa. And then there were also, on top of all of these really cool variations that we wanted to study, there were a lot of other variations that were stable. Okay. And so we started learning that we had both disturbed systems, disturbed variations, and we had what we called quiet variations. Okay. So we began to create categories for the disturbed indices and the disturbed current systems, and the quiet current systems. Okay. And one of the biggest that we have, and sadly, look, what we learned is that a lot of the quiet systems, the quiet variations, it ended up eclipsing, or could very well eclipse, the disturbed ones. Not just in magnitude, right? But also in time or in space. So we had to learn how to subtract out some of these quiet current systems, simply because they would engulf everything else. The nice thing, though, is that typically the disturbed systems were on a much higher, much faster time varying scale, and the quiets, and oftentimes very stochastic, or so it seemed. And the quiet ones were actually quite linear, quite gentle, slow moving, right? Not very quickly moving. And they would always be spatially stationary, essentially. Okay. So we'll talk a little bit about that. Now, the largest one, of course, is the solar quiet. We call it the SQ variation. Okay, so let me make sure I've gone through these. Yeah. So the induced currents on the ground, or induced variations on the ground, we separate them into quiet and disturbed condition, or disturbed variations. And we're going to talk about one of the biggest ones. We're actually going to talk about only about two of the quiet systems. And the reason why is there's more of them, but these are the two biggest ones that we want to subtract out. And the reason why I want to show them to you is just so that you understand that when you look at magnetometers on the ground, so if anybody who actually wants to grab a space weather station, for example, right? I know HAMSI, for example, is creating these space weather stations. That's wonderful. That's great. That's fantastic. But don't think that you can just take a magnetometer station, grab it, and suddenly you've got something that you could throw into, let's say, the K index. You can't really do that because there's a lot of other systems. As I just kind of went through all of that review and showed you how complicated things are. Well, in order to get to that data, that pristine data that we use as indices, there's stuff that has to be backed out, okay? And things that has to be calibrated out and detrended, okay? So I'm going to talk about two of the main systems that we use, that we detrend, that we take out. But you'll very, very quickly can imagine why they're there. And the first one, of course, is due to the sun, right? That's the solar quiet variation. And it results primarily from currents flowing in the E layer, okay, of the ionosphere. One of the reasons why is because it's extremely dense. Obviously, we're talking about the E layer. We're not going to be talking about the D layer because the D layer, for the most part, is pretty neutral. The E layer is where you actually have charge that stays ionized all the time. Recombination is slow enough, if you recall from maybe a couple courses back when I was showing, I think, some of Frank Donovan's charts, and I was talking about some of the recombination processes that were occurring in some of these layers. The E layer was really allowed you to have a standing layer all the time that had a decent amount of free-flowing current. And so the solar quiet variation occurs when the sun is shining on the ionosphere and is consistently ionizing a certain part of of the ionosphere, and it peaks in the E layer. Okay, so we'll talk about that in a second, how we've subtracted out and what it looks like. Yeah, okay, I talked about the coupling of the upper atmosphere. I'm trying to see what else do I want to say on this chart. Many indices have been derived in an attempt to isolate the magnetic variations associated with these different current systems. Yes, I've been talking about that, so I think I've covered everything here. So the main current systems and the corresponding indices, and you're seeing here, we're going to talk about, hopefully we'll get through all of these today. I don't know if we will, though. So at low latitudes, we have the ionospheric wind dynamo. This is not solar wind, I almost said solar wind. The ionospheric wind dynamo. We have the SQ variation. And it's really, even though we call it the wind dynamo, it's really about a few tens of nanotesla. And the variation is extremely smooth. Okay, and we'll talk about the L variation in a second. Do I talk about that in here? No, but we will. The L variation, as you'll learn, the two quiet systems that I want to take out. One is SQ, the solar quiet variation, because the sun is a huge part of our system, right? What do you think the other one might be? It starts with L, right? How about lunar, right? Because we've got another really big body that might actually cause variations because of the tides. And sure enough, we do. So the two big current systems, the quiet current systems that we need to remove, are the solar quiet variation and the lunar. And they don't call it LQ, they just call it the L variation. But these are some of the biggest perturbations that we see. The nice thing is that they are very smoothly varying. So they're reasonably easy to take out, okay? So the SQ system is about tens of nanotesla, and I'll show you an example of it and how we have to remove that before we derive, let's say, the K index, or pretty much any of the indices that we use. Okay, we also have the high latitude ionospheric current systems. These are disturbed indices. We've talked about them before, the AE index, right? The AU, AL, and AE. We will talk about it again. Perturbations are hundreds up to even over 2,000 nanotesla. And we have, there are multiple sets of stations that we use. I'll talk about those in detail in a little bit further as we move along in the, after I talk basically about how to subtract out the quiet stuff. Then we'll talk about low latitude. So here's high latitude, here's low latitude. That will be the DST index that will mainly characterize the ring current. okay? A little bit less than what you'd expect for the auroral electrojet, so we're not in the thousands of nanotesla, just in the hundreds of nanotesla now, okay? So a lot more crazy deviation here than you see here, okay? And smaller number of stations that are being used. And we'll talk a little bit about why. And then we'll talk about the mid-latitude KP index. So we've got high latitude, low latitude, and mid-latitude, okay? And I'm putting this in this order on purpose, because you can understand that when you talk about a KP index, which we're talking about, the P is planetary, okay? The reason why we call it mid-latitude, but the reason why it's used so much to get a global understanding is because it's kind of got a little bit of what's going on here and kind of a little bit of what's going on here, but it's not dominated by either. Okay, so it's not a high latitude index, it's not a low latitude index, it's mid latitude ish, but you'll see the stations that it uses kind of has a little bit of effect from both of these things. So it becomes a great index to kind of get a planet to feel for how the planet is reacting as a whole. But as you can imagine already, just with that small little bit of knowledge, why the KP index may not be the best index to use when you're looking for things like aurora, right? It's a planetary index. It's not really set up to be looking for things that are happening just in the auroral zone. So gives you an idea of really already why you need to be looking in certain areas for certain things. Remember, because we talk about the ring current is going to be the energy storage, right? But it's not going to show you necessarily what's going on in the auroral zone. It's going to tell you what's going on with big geomagnetic storms. So that's going to be important for certain understanding of what's happening on the surface, especially for sustained and strong fields. And we'll talk about how that really kind of couples into things like, maybe the power grids, right? Or maybe even scientific understanding of what's going on in the Earth's magnetic system. Whereas if you're just someone who's looking for aurora and you want to get a good show, well, maybe AE is a better index for you to use. Okay. So let's move on to that. Oh, before we move on to that, hold on. Let me make sure I remember how this is organized. Okay, I'm just going to go into the coordinate systems first before I go into the quiet variations. All right. So another subtle aspect of these current systems, and you need to understand before we get into it, really is how are they, what is a coordinate system that we're using? Those of you who recall the M series, remembered that I talked very much about the GSE coordinate system, right? And sometimes I might have even gone into the GSM coordinate system. Well, these are wonderful coordinate systems if you're sitting out at the nose of the Earth's magnetic system, right, the Earth's magnetic shield, and you're trying to get some type of understanding of what's going on between you and the sun. Because you're seeing how the sun's magnetic field, the solar wind, ends up impinging on the Earth's system, and you know how much of the sun's magnetic field and the solar wind is reconnecting, right? Is merging with the Earth's magnetic field, and then obviously pumping and dumping all of its energy inside the Earth's magnetic system that then can create these geomagnetic storms. But all that goes away when you get on the ground, right? Because as soon as you're standing on the ground, well, depending upon where you're standing, all amateur astronomers know this, for example. If you see a picture that someone is looking at, from a telescope, someone looking at the sun, if you're in a different latitude, right, a different hemisphere, your picture of the sun, your view of the sun when you stare up in the sky is going to be radically different than someone who's located at a different point. And the reason for that is because once you get on the ground, the direction that points up changes, right? I mean, if you're sitting on the ground up north, looking straight up could be your North Pole. If you're on the South Pole, looking up could be straight south, right? So your version of north or up changes dramatically. Well, great. Welcome to the ground. Okay. So imagine if you define a coordinate system based on the surface of the Earth, you're no longer in what would be considered an inertial reference frame. This is not a coordinate system that we're about to define. This coordinate system is not one that is stationary relative to, let's say, the GSE coordinate system or the GSM coordinate system. This is a relative coordinate system that is based locally on the ground. Okay, and it changes depending upon where you are on the surface of the Earth. Because what you're defining, right, is basically where straight up and straight down is. Okay, I mean, obviously, straight down is this direction, but straight up would be looking, nadir, right? Zenith and nadir. So understand that this coordinate system does require you to have some level of understanding that Earth isn't flat. And I know that's going to upset all the flat earthers out there, but it's really a local thing. And if you really want to get a global understanding of magnetometers and how they work in different, when you stack them all together, if you don't know where your latitude is, what latitude you're at, you could easily get yourself confused. Okay. In fact, in many places, as you'll notice, even when we subtract out quiet variations, you'll notice that perturbations that go one direction at one latitude will reverse and go a different direction in a different latitude. And some of that has to do with the coordinate system, and some of that just has to do with the way current systems work across the equator. But locally, when you look at magnetic indices, okay, and if you look at the raw data, okay, so now we're not looking at like a KP with a bar that just gives you a number, 3, 4, 5, whatever. You actually go to, let's say, the actual magnetometer station where you're dealing with the actual numbers and you're actually dealing with an actual, vector, right? A magnetometer will measure the strength of a magnetic field, but it will also measure a direction of what that magnetic field is, the way it's pointing. And the variations that we're measuring are, how that vector, how that direction changes in time, but also how strong does it get, right? So we're measuring multiple different things, and we call those vectors, right? So we organize that on the ground by looking at, obviously, seeing this blue vector. This is just the field, the magnetic field direction. Okay, imagine that vector coming in, this magnetic field with a direction and a strength pointing in some random direction, okay, for a moment, a snapshot in time. But at your location, downward, let's say, we're going to say Z. Okay, we're going to define it as Z. So that's straight down. You're standing, and you're putting your feet to the floor. As you go straight down to the ground, that's Z. That's the Z direction. Okay, so that would be considered nadir, I guess. Right, zenith would be the opposite. You look straight up. Okay, so then you go X. We're going to take the X direction as the northward direction. Okay, we're going to take that as northward. Y would be eastward. Okay, this is on the ground in your local, place. So I don't want to hear somebody from the southern hemisphere saying my northward direction and my eastward direction are totally different than yours. Of course they are. Or someone at a different local time saying my northward and my eastward direction goes this way, and someone at dusk says my eastward direction goes that way. Right, because the Earth is round. Things are going to circle. So if you define your three axes as downward, eastward, and northward, then you are able, okay, and that would be X, Y, and Z, okay? Then if you get a vector that comes in as a geomagnetic field, whatever direction that is, you can do really cool different mathematical constructs and grab different angles, and we'll talk about it just a little bit, not very much. But what you are searching for is the projection of this vector, the magnetic field direction, along the surface of the planet. And that is going to be your northward, eastward, in the plane that the north and east vector makes. Basically the plane of the ground in your local system. You don't care so much how much of that magnetic field points into the Earth. It's not super important to you. What you care about is if I'm, for instance, a magnetic field vector, how much am I wiggling? How squishy is my dance? Okay, you want to know the direction back and forth that my magnetic field line is making. The reason why is because the direction which is now parallel to the ground, okay, that direction, this way or this way or this way or this way, but whatever direction is parallel to the ground, right, in this plane, this XY plane, however much this field is wiggling in this plane, that is what's going to dictate how currents are induced. That's going to dictate how dramatic things get in terms of how strong a variation, how much disturbance is going on way out there along that L shell, out near the solar wind area, how, as that's coming in, how dramatic that change is, and then therefore how much of a current and electric field can I induce in the ground beneath me. Okay. So that's why we care about the H component more than anything else. We don't care so much about the part of this component that is from here to here, the vertical. We don't care so much about this component. Now, some of our work does, especially academia. But for the layman, for people, non-experts, for people who just want to know how disturbed is the Earth's magnetic system at this L shell, H. Okay. And even when we look at indices, you'll see it, all of the indices, H plays a massive role. Okay. So here's another version of it. Here's your Z. Oh yeah, they got nadir and zenith. Look at that. You know what? I've never noticed that in this diagram. I have never noticed that they have nadir and zenith. Zenith this way, nadir this way. But here is Z. Okay. Y, they're pointing east. West is minus Y. North is a plus X. All we care about when we talk about that geomagnetic field, whatever direction it's coming in, we don't care so much about this downward component, not so much, but we sure care about this H component. Okay. Now, if you really want to know, because the other things that are captured is you have the change in, if you're looking at this magnetic field, the projection of this field, okay, into the horizontal plane, into the XY plane, but its deviation from pure north. That is an angle. This is called the declination angle. Okay, so how much is that horizontal component of the Earth's magnetic field that's pointing in at your local place? How far off of north is it, of true north? That's the declination angle. And then the same thing, the inclination angle is how much does it deviate? Does that H component deviate from the surface of the Earth? No, I shouldn't say H component. How much does the magnetic field itself deviate from the surface of the Earth? That's the inclination angle. Okay. But again, in practice, D and I aren't going to be things that you'll use very much. If you were in academia, you'd probably use them a lot more. If you were a magnetospheric physicist and really studied this stuff. But when you see things listed in, I don't know, the USGS, for example, or if you go to a magnetometer station, you look at SAMNet, or you go and look at Intermagnet website, you will see HD, Z, X, Y, Z. You'll see I and D listed. This is what they are. Okay. And remember, latitude of the station matters, because this is not defined the same for every single thing. It's defined locally. Okay. And how you start is, what is your zenith and what is your nadir? What is your east and west? What is your north and what is your south? That is the basis, right? The basis set even, but the basis for everything that comes after. And getting the H component, how much the magnetic field wiggles on the surface of the planet, right? How much back and forth, how much is the magnetic field dancing? That's what's really critical. Okay, hopefully no questions on that. I don't mean to poke that into the ground, but hey, This is not always an easy thing to understand. Okay, it looks like everybody's got it. Okay. So let's talk a little bit about the solar quiet system. Right, we were talking about how we were going to end up needing to subtract this off. So let's talk about how it actually is formed, what it does. So as you can see, hopefully you can recognize this as Earth by now, right? You can recognize the shaded section as being the night side of Earth, where this is the sunlit side. And as you have the sun hitting Earth, it's going to create these variations. In fact, as you can tell right now, the way they have it angled is that this is a period where it looks like they have this angled in such a fashion that this is northern hemisphere summer, right? Because you have a lot more exposure in the northern hemisphere than you have in the south. So this is a current system that is driven because of the ionization of some of the photoionization of the sunlight. It mainly affecting the E layer of the ionosphere, and that has to do with the atmospheric chemistry, very much so, with the recombination rates versus the ionosphere, the ionization rates. And it's driving, obviously, on the sunlit side, it's driving a current system in this case that is going to be maximized. Well, it's going to be centered rather on local noon, right? But it's going to extend, in this case, into the dusk region and into the dawn region. And in the southern hemisphere, it's going to have the opposite vorticity. Vorticity, is that the correct current? I don't know if I can say that when it comes to current systems. I'd say opposite direction. I'll be more careful here. That's a too creative use of the term, I think. But so it has the opposite sign, right? The opposite direction in each hemisphere, and it's a slowly varying system. So that as really because it's basically time stationary, right? It just stays here, and as Earth spins underneath it, you basically go from a region that is experiencing, let's say, none of the solar quiet, as you will on the night side, to experiencing it in this case near dawn as a southward component, and then as you move toward noon, it will be a duskward component. And then as you move toward dusk, it'll be a northward component. So you're going to slowly see the effect of this current system change the direction of the magnetic field over time, right? You're going to see, remember the H component of the Earth's magnetic system. We're talking about that H component here. This will slowly change. It'll have a perturbation on it, but that perturbation will be slowly varying. And it may not change it all that much because it's an additive component, right? It's not that big of a variation. What do we say, tens of nanotesla? Not huge, but significant enough that if you started seeing it go down or change, you'd want to subtract it out because it's not something that is to do with space weather, like a transient disturbance in space weather, right? It's a quiet variation. It's going to happen all the time. Now, as you can see, much of it is low, middle to mid latitudes, right? And it's so low because it's in the upper ionosphere that it's shielded mainly from the current variations that we saw, right? We're even talking about lower in the plasmasphere. So it's actually really shielded. It's shielded from ring current, for example. And for the most part, because it's low enough, it's not being affected too much by the auroral current systems. But there is a little bit of coupling. But for the most part, because it's so low, it's mainly just the ionospheric wind dynamo. Okay. There is an effect from the neutral winds in the thermosphere. Current system is located between 90 and 200 kilometers. Remember, aurora does occur here. Occurs even lower than this. So there is a little bit of coupling, but it's still quite well resolved. And also it will be not just seasonal, right? Because you do get seasonal changes, but you also will get solar cycle changes. If you recall from, oh goodness, what did I call it? The H series? Heliosphere? I think I probably called it the H series. That was when we were talking about the solar cycle variations in the breathing heliosphere. And so you could see over the course of time how radically different the Earth's upper atmosphere would change, because you do get much more ionization during solar maximum than you do solar minimum. And that will change. And then also the seasonal influences can also cause this to change, because you do, believe it or not, in the wintertime, have different total electron content than in the summer. So that will change things as well. So it's not always something that is always the same amount all the time. What does make it the same amount or the same is that it's spatially well resolved. Okay, so the variations are slow and spatially extremely consistent, right? Day-side ionosphere. So here's a picture of the contours for the SQ system, and here is a very old paper that is showing the subtractions of many of the current system the variations of the current system over local time. So this is 0 hours, 4, 8, 12. So here's local noon, 16, 20, 24. Okay, and they do it again, and they do it again. For the northward component, right, this is the x component, the eastward component, that's plus y, and the z component. Okay, so we're talking about delta x, delta y, and delta z. These are stations. Okay, magnetometer stations. Get used to this. This kind of stack plot is very, very common in space weather. We're looking at geomagnetic stations. And here's their latitude. Almost 64 degrees, 62, 60, blah, 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 all the way down to 0 degrees. Sadly, we don't, and you will always see this. There's almost never as many stations in the southern hemisphere as we have in the northern hemisphere. So you'll see so much more. This is where all the people are. So we have all over the world, we have far more people in the northern hemisphere. So we're always underpopulating the southern hemisphere. But notice, again, these current systems do this, right? Or this current system does this. Local time moves the whole map underneath this current system. So imagine me taking the map of the world and pushing it this way, right? So as this system, as the map moves this direction, right, you're going to see in the northern hemisphere deviations going southward, then deviations going, what is this, eastward? And then deviations going northward. Hope I got that right. Did I get that backwards? And then the other way. In the south, you'll see the opposite. So you're going to expect to see, especially in the eastward-westward direction, you're going to see things flip, right? And you're also going to see them flip in the north and the southward direction. So when we look at, let's look at that. So in the north and southward direction, you're going to see in the northern hemisphere, you're going to see peaks right around local noon, right? In this case, a negative deviation, right? But it's going to peak to a great degree in and around mid-latitudes. And it's going to get smaller as you move to smaller or to lower latitudes, or it'll get smaller as you go to, let's see, it's the northward direction. Yeah, I believe so. Wait, is that how it works? I have to remember. I can't remember. There's an area in mid-latitudes or at higher latitudes or something like that where it minimizes. And that's because you're going through this region here. And then, so that's in around 50 degrees, I guess. And then, of course, as you go to the southern hemisphere, things change. Okay. Now, granted, here they're showing a big peak, and that may be because it was, I don't know, maybe it was southern hemisphere summer. I'm not exactly sure, but you can see it's a massive peak here. But as you can see, things change. It goes from one direction, from a northward direction, a negative direction, southward direction to a northward direction. Now, when we go to the east and west variations, again, you're going to expect to see a switch as you go across the equator. And you do, right? You see it going basically positive to negative at northward stations. And then you see in the southward, in the southern hemisphere stations going from westward to eastward, from negative to positive, right? And you'd expect that because you're going from a system that's doing this to a system that's doing this. Did I do that the right way? Did I do that the right way? They're going like this. I get confused. I'm sorry. My apologies. But as you'd expect it to switch from one hemisphere to the other. And in the vertical direction, you're seeing it basically peaking, and then it switches here, and I'm not exactly, because you're going vertically. So you're penetrating into the plane of the page. And I'm not really sure how it works vertically because I've never studied the SQ system. So, but you do see, once again, it peaks around local noon where the deviation is. And remember, these are delta changes. So these are not just the actual, the full variation. These are just how much things change from whatever the baseline is at that time. And here, I believe this is 0 to 50 nanotesla, which begs the question as to why this one's so large. I don't really know. And I haven't read this paper in so long that I don't recall why they were talking about, if they even mentioned why this one changed so much. It may be just calibration. But what is important to see when you look at this is not only do the variations peak at midday, but they change, of course, across hemisphere, and they're slowly varying. This is what makes it possible to subtract this stuff off. Okay. So again, if you have a magnetometer, right, or if you plan to put a magnetometer on your system or your house, or, some people want to do this. They say, hey, I'm going to get a space weather station and I'm going to use this magnetometer stuff. This would be great. Just realize you're going to have slow time varying things over the course of hours on a daily basis. And unless you know to subtract out these variations and what they are, it's not going to be, it's a non-trivial thing. Now we talked about the solar quiet. How about lunar? As you can imagine, the lunar variation is also going to be very slow varying, right? Because you're dealing with, but you are once again, because you're dealing with tides, right? You're dealing with a tug, not so much that the moon is ionizing anything. I mean, granted, it's got an albedo of its own, sure, but it's not going to be ionizing the upper atmosphere to any great extent. But in this case, what it's doing is that it's actually using gravity, and it's tugging on our atmosphere. And just like it tugs on the water, right, and creates the tides in the water, it creates tides in the atmosphere as well. Kind of crazy to think that our atmosphere actually swells and breathes in and out, so to speak, in response to the lunar tugging, but it does. I mean, the moon is a very large body, so it does have that effect. And so it's changing the scale height of the atmosphere. It's changing the density of the atmosphere, and therefore changing the density and the scale height of the E layer, right? And so that is going to just in of itself cause current variations, cause conductivity changes. And it's not, honestly, you're going to think about the moon circling the Earth, right? So there's going to be a 28-day variation, granted. But the bigger variation is the 24-hour variation that occurs with the Earth rotating, right? Because the moon is, from our perspective, it looks like the moon is rotating the Earth every 24 hours. It's really us moving. But it causes, once again, a very slow and yet purposeful and obvious variation. This time, it's not located, spatially located in only one time, in one set of local times. It's not peaked at any one local time and therefore stationary, right? It moves. And it's an effect that is pretty, I don't want to say it's obviously not linear, but it's very smoothly varying and periodic. Okay. So again, in our H, our horizontal component, our Z component, which is the vertical, the nadir and zenith component. And in this case, they're talking, I believe in this one, they're using, this isn't a declination angle, but they've got it as a D, I believe this is the east-west component. And in this definition, I forget what D is, how D is defined, but it's not an angle in this case. Or is it? They're doing it in north latitude. They changed it into degrees. They are, yeah, in this case, I guess they are talking about it in degrees. So the D is the declination angle. The Z, I'm not sure if they've changed this into, because it isn't the I angle. Nonetheless, there's still components. And again, I don't use any of these, so I can't tell you all the absolute details of it, because this stuff for me is all subtracted out, right? Because I don't look at the ionosphere from this perspective. I don't need to. But just knowing that it's here is something, and knowing that you're going to have to deal with it from a space weather perspective if you decide to, get one of those really cool space weather stations. Just know that this is the kind of stuff that has to be subtracted out. Okay. Now, again, these are thermally driven tidal oscillations, and it's because of the scale height and the scale change, the changes in the upper atmosphere due to the gravitational effect of the moon. And you're going to get oscillations, right? That will change depending upon if you're in the northern hemisphere or the southern hemisphere. Once again, I mean, it's ionosphere. We're talking about things that are co-rotating. So you're going to expect to see the variations change. And it's going to peak, in this case, it peaks in the H component, it peaks at the equator. Here we get something that zeroes out at the equator, but it's strong variations on either side. And I'm not exactly sure why. It has everything to do with the fact that this is a vertical component. So the way the magnetic field is coming in, you're not getting a lot of magnetic field penetrating the Earth's magnetic system at 0 degrees, right? Because, I mean, most of that field is coming out the other way. It's coming at higher and lower latitudes. So, and then the same kind of thing happens in the D component. You get, once again, a flip, okay? But these are very low, slowly varying, and very easy to subtract out if you know what to subtract out. You have to know that they're there, okay? And it's about 10 to 15% of, so it's even less than the solar quiet variation, which is only on the orders of tens of nanotesla. So this is even smaller variation than that. But if you don't know what you're looking for, if you think that you might actually be looking at something that is space weather related from a transient observation, you might make that mistake. So again, these things are pulled out of the data before you look at the indices like KP, like ring current, like, AE, all of those, and all of the different types of indices that we're going to go into here in just a second. And I just wanted to, I'm sorry I'm not as much of an expert on those systems as maybe I should be, but I'll just put it on the myriad of lists of things that I need to, get a better understanding of, and don't, because there's just so many things. I mean, this is why heliospheric, the only people who should be teaching these subjects are people who know heliospheric physics, because they wouldn't even, most people wouldn't even know that we had variations like this that need to be subtracted out, right? And here I am, I can hardly teach them myself because I don't know them very well. I just know that they exist. It's just so much. These fields are just so extensive. Okay. So once you clean the data, and I have not gone into all of the different quiet variations and quiet systems that can be subtracted out, depending upon, as you can imagine, depending upon what type of variation that you're looking for and what type of transient disturbance you're trying to isolate, there are other things that you may need to subtract out. And that's even before you go into looking at your local magnetic system, your local magnetic environment, and subtracting out, the bridge over there, or the car over here, or the garage, or the electric generator you've got over here. I mean, all of those types of systems locally can cause disturbances as well. So it's non-trivial to get a magnetometer. As easy as magnetometers are to build and to buy, it's non-trivial to get a magnetometer installed that is going to give you robust measurements of pristine measurements of the Earth's magnetic system without contamination of one kind or another. Okay. All right. Hopefully I'm not drummed that into the ground. I probably have. Sorry about that. So let's talk about, let's jump into some of the indices from a perspective that we already have, we'll do the easiest one first, which was the AE indices, because these indices are ones that you know, right? That we've already talked about in the ionospheric regime just a little bit. And you hear people talk about the AE index, but really what they're talking about is kind of a group of indices. The AE index, the auroral electrojet index, is comprised by the AU, the AL, and the AO. And really, it's all based on the upper auroral electrojet and the lower auroral electrojet. So AU is upper, AL is lower. And we're really talking about the eastward and the westward electrojets because there are two of them. And when you look at these data indices, obviously we're talking about aurora, right? We're talking about magnetometer stations that are high latitude. Okay, so here they all are. These are the ones that are being used. And if anybody needs to go to, this is oh, come on. Do I have it? Let me see. Shoot, I don't think I have it listed. Okay, the Potsdam website. It's a really good place to get this. This is all of this data that I've got here is from Potsdam. And they've got and I literally have lifted it off, all this information here, right out of their website. It's a wonderful resource to go to when you want to learn more about where magnetometer stations are and why the magnetometer stations are used the way they're used. But as you can see here, this is a set of stations. How many stations is this? Is this 12? Where does it say? Yes, 12 observatories. 12 observatories, there we go. Made of 12 observatories in this zone. Now, notice they're all northern hemisphere. And the reason for that is because it's a lot easier. There's a lot more people up here to monitor these stations than there would be trying to put them all in Antarctica, right? A lot harder to get to, a lot colder, a lot more difficult to deal with, a lot more remote. So these stations for the AE index are all northern hemisphere. But notice that they're all spread out in local time. Okay, that's super important. They're not just located at one longitude, which would be one magnetic local time or one geographic local time. We need to know what the electrojets are doing at all the way around the globe. The nice thing, though, is that most of the stuff is conjugate. So in other words, whatever happens in the north is mirrored in the south. So having all these stations in the northern region here it doesn't prevent people from in the south from getting accurate estimation, because really the aurora and the disturbances that we see, remember when you think about L shells, right? You're thinking about the particles that drift, that bounce and drift and gyrate. They are going to both poles. Not both poles. They're going to both mirror points. We call mirror points in the Earth's magnetic system. So they extend both in north and south, and we call these conjugate points for that reason is because the particles that are there and the distributions of particles that are in a particular L band, let's say, they really are bouncing from north to south. So you will see almost exactly the same type of distribution at both sets of latitudes, right, at conjugate points both in the north and the south. So you really can characterize what's going on in the south from what you see in the north. Now notice these regions are anywhere between about 75 degrees north to almost, a little bit below 60 degrees north. Okay, we're not talking totally in the auroral oval. This is a subarauroral. Okay, we're talking about typically in a quiet time, the auroral oval is still up here. So this is something that the region 1, region 2 currents, this is not the region 1, region 2 current system. This is below it for the most part. Sometimes in big storms, you will see the region 1, region 2 current systems open, the auroral oval open up to the point where it's swamping these stations. And we will see what happens when that does happen. If we actually had magnetometers in the auroral oval measuring those current systems, oh my goodness, they'd be swamped so fast, so often, that there'd be very few instances where we'd be able to make sense of it. What we actually do is we end up coupling a lot of that stuff. A lot of the activity from the auroral zone ends up coupling into these subauroral stations. There is we've talked about that a bit in the ionospheric classes where we talk about how the region 1, region 2, you have a lot of, when the particles precipitate in, you get a lot of heating, right? Joule dissipation, all that kind of stuff. And that heating in the upper atmosphere actually does drive winds, and it couples thermodynamically, couples into vertical winds and vertical convection patterns that then through things like gravity waves can actually then propagate and cause disturbances down in here. And I mean, sorry, I should be up here. Propagates and causes disturbances down in here. And that's part of how the electrojet is part of the dynamics of the electrojet. Let me just put it that way. Okay. So when we look at the AE index, we are mainly looking at something that is an auroral process, even though it's slightly below. Okay. When you look at that index, it is about a 1 minute index. But way back when it started back in 1957, it wasn't a 1 hour index. They've now made it much more robust. And there are varying times. That's one of the nice things about Potsdam is that they tell you when the index was available, really high res, and when it wasn't. When you look at how these stations are either averaged or used, you have the upper index, right? The AU index, which I think is that the westward electrojet, and then the AL is the lower index, that is for the eastward electrojet, and then you can get the AE index, which is basically an average, which is, I want to say, I gotta be careful, not the average. AE index is basically the envelope that talks about how if you have the upper index being completely disturbed and you have the bottom index, the lower index being completely disturbed, what is the difference between them? And that becomes AE. Okay, so it's AU minus AL. And then if you want the average, what is the average disturbance between the AU and AL? That's AO. Most of the time we end up using AE because we want to understand both how, what is the massive amount of disturbance, that'd be the biggest part of the disturbance, biggest part. I'm not very good at with words today. I guess really what I guess I just have to say the envelope. So if you get a little bit of disturbance in the upper region, but in the AU, but you're getting massive disturbance in the AL, you're going to be able to tell what the difference, what the delta of that disturbance is using AE. If you use AO, you're going to potentially average out. You're going to, because averages have a tendency to kind of to weight extreme numbers more and in a funny kind of way. And so you may not be able to encapsulate the amount of disturbance that you're seeing very well by using AO. AO I don't want to say it's a climatological index, but it's used in a slightly different way. If you're an aurora observer, AE is probably the best one to be using, simply because you get that. I forgot I had this chart. Because you end up being able to get that entire envelope, that entire delta between both the eastward and the westward electrojet, and you're not smearing out what one is doing and trying to smash them together. You're getting the full, almost like the full dynamic range of what's going on between the two, and that's why AE is so nice. It's a bit more sensitive. So if I should have pulled this up a little bit earlier. So when you look at the location of these indices, or the location of these magnetometers, and you kind of measure where are they in L shell, right? So you can kind of see when you look at where they are between 80 and 90, you're looking at L of 5, L of 6 maybe, right? You're looking way out there, definitely higher than the United States, right? Here's the US down here. So you're definitely looking way up here. So L of 4 at the least, L of 5 likely, L of 6, right? You're beginning to get beyond the ring current, okay? It's almost completely excluding the ring current, right? Which we know is the ring current sitting, centered right around L of 4. So we're not going to be looking at things that have to do with big geomagnetic storms, where the energy storage ring of the Earth's magnetic system is. We're going to be looking at things that are further out in the Earth's magnetic system, right? And that's what this is for, right? Here's the ring current here centered at L of 4, right? But we're not looking at that. We're looking closer, much, much closer to regions, region 1 and region 2 current systems. outside of the ring current, things that are a bit more easily disturbed. And if you remember back with the M series, we talked about when big solar storms, big CMEs come in and they take those high L shells in the Earth's magnetic system and they peel it back. Remember the chicken dance? Remember I told you doing the chicken dance, right? So we peel back those high L shells and fold them back and fold them into the tail and then shoot particles up the tail. Well, those are high L shells that are dealing with that, right? They're on the front end of the Earth's magnetic system. So those high L shells are going to be far more disturbed, even the ones that aren't being peeled back. They're much closer to the disturbances. And so they're going to be that much more rattled, as we call it, as they're being, as they're moving closer and closer and closer to being the front edge of the Earth's defenses. And so this whole area is going to be far more impacted and far more disturbed. So you're going to expect that any current system that's dealing with that, and any magnetometers that are sitting out here, right, not in the heart of the Earth's magnetic system, but way out here at high L shell, these are the ones that are going to be kind of on the front lines of telling you if there's some type of geomagnetic disturbance, right? Including disturbances that aren't necessarily sustained. So substorms, anyone, right? Whether they're driven by things in the solar wind, forgive me, Larry Lyons, or not, because there's a big argument still to this day, I believe, whether or not substorms are driven by things in the solar wind or if they're just triggered by internal reconfiguration of the Earth's magnetic system inside itself. Because obviously there are processes going on inside the Earth's magnetic system all the time. And those systems, those disturbances can trigger a reconfiguration, what we call a dipolarization. And so substorms can excuse me if you hear my daughter playing in the background, those reconfigurations can cause substorms to occur, right? And that doesn't even matter if the solar wind is doing anything. But those substorms are going to be registered by high L shell stuff. Okay. And so you're going to see those substorms very, 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 see these small perturbations occur at very high latitude systems. So the AE index is perfect for that. And it's also, and I'll show, I think I'll show in the very next slide. Yeah, I'll show examples of substorms. So hopefully does this make sense to everybody? I hope. Do the results of the ground magnetic perturbation be more precise with magnetometers on the ground or with satellite observations? Oh my goodness. That's a really good question. And honestly, when you're talking about ground effects, it's going to be the ground, but bar none. Satellite observations, it depends upon where you are. And so, for instance, if you're upstream, if you're in solar wind, then you get a better idea of what's coming and whether or not you're going to be disturbed. But satellites in the Earth's magnetic system have a hell of a time when it comes to the Earth's magnetic field and trying to understand what's going on, because you've got L shells moving back and forth over you at all times. And honestly, I honestly do not know that many people who look at the Earth's magnetic field inside the Earth's magnetic system. They look far more at particle distributions, and they look far more at currents and waves, because they get a better feel for what the particles are doing as a whole. Trying to look at the variability of the Earth's magnetic system at one single point in space inside that system, it's a nightmare. And maybe if there's any magnetospheric physicists watching this and laughing at me, they say, well, of course she's saying that because she's a solar wind physicist. And I say, right. There's a reason why I'm a solar wind physicist, because the solar wind actually has some level of order, and it's easier. It's honestly easier. Even the most complicated stuff in the solar wind is a bit easier to understand from a magnetic field point of view than looking at local perturbations of the Earth's magnetic field inside that system. So looking in situ at the magnetic field in let's say a geostationary satellite, for example, uh, unless you have a whole slew of them or a small constellation of them, it's really difficult to get any sense of what's happening. That's why when you see um, magnetospheric constellations or magnetospheric missions, for example, like MMS or Cluster, or even the Lanol satellites in GEO, you'll see so many more, if they're invoking magnetic field measurements, you will see far more of them have multiple satellites that they're then looking and comparing the magnetic field observations at a group of satellites, as opposed to just looking at one. In the solar wind, you have a hope of understanding things from a single satellite observation of the magnetic field. In the Earth's magnetic system, you better have a group of them or you could be in real trouble, because there's just so much going on, right? You're sitting in that egg beater. Remember we talked about second chef is constantly got its mixers going, and you're sitting in that bowl of, the mixers going all the time, and you're trying to make sense of it. It's so much harder. And I think I even mentioned this not that long ago in one of these classes, where I was blown away the very first time I started doing magnetospheric research, and I saw that the radiation belt physicists, they were looking at and doing their studies with a model magnetic field. They were using like the IGRF or the Sigonenko model. They weren't using actual magnetic field measurements aboard the spacecraft. And at first I thought, that makes absolutely no sense to me. But then when I took a look at the magnetic field, I went, oh, okay. Magnetic field was just all over the place. So, yeah, I mean, that's the best answer I can give you. And it's just an extremely complex thing to look at. And unless you're very, very savvy with what is happening and you're looking at lots of different instruments from multiple spacecraft, you have a heck of a time in the magnetosphere understanding exactly what the magnetic field is doing on a larger scale. Whereas in the solar wind, it's a little bit easier. You can extrapolate a lot more readily than you can in the Earth's magnetic system without models. You can extrapolate better. The Earth's magnetic system, you definitely need those models to help you. So I know that's probably an unsatisfactory answer, but that's the best I can give you. So hopefully that helps, Margarita. Do you know about zero stage? No, you'll have to explain. I don't know what about zero stage is. Is the North Pole really shifted? Yes, well, not the geographic North Pole, no, but the Earth's magnetic field is shifting because the dipole field component of the Earth's magnetic system is weakening and will flip eventually. But don't worry about it. The sun does it every 11 years, so the Earth knows what to do. Like I said, all you have to do is look at the sun. Every solar maximum, you're looking at a dipole field shift. So anybody tries to tell you that this is crazy and it's Armageddon, laugh at them. Say, okay, I'll see you in another 11 years, because it's just silly. This does happen. It's just a lot more slow when it comes to the Earth's magnetic system. But it does the same thing that the sun does. So don't worry about it. For real-time radio propagation, do we have to add back in the slow variation to better understand the daily cycles, day and night? Wow, that's a great question, Phil. Huh. That is probably not a bad idea. I wonder how many propagation models actually add that stuff back in. I would think that would be a savvy thing to do. I would think that would be an easy thing to do, because those variations are so unbelievably stable. Yeah, so maybe in the future, if they don't do it yet, and I don't know, because a lot of these propagation models, they rely on other ionospheric models like MSIS and CTIP, and so you might check to see. And I don't know off the top of my head, because again, I'm not an ionospheric physicist. I don't know specifically how MSIS adds in all their adds in what variations they add in, and it makes assumptions of other variations. But I would think that the seasonal and lunar variations and solar quiet variations would be very easy to add into these models. So I wouldn't be surprised if they had them. And if they don't, I think it would be a really good question is to ask why not. Because yes, they absolutely will make a difference when it comes to radio propagation. You know, um, absolutely, they make as much sense as obviously as a diurnal variation. Period. Um, so Uh, and the only way that they might make a little bit less, and why people might have omitted them, is because they are smaller, like the lunar, right? The lunar variation is only about 10 to 15% of what the SQ, the solar quiet variation is. But when the solar quiet variation is on the order of 10 nanotesla plus, I don't know how that translates into current systems in the E layer, but I would think that would be non-trivial. So. Um, And I bet you the SQ variation is in there in a lot of the propagation models, but I'm not sure about the L variation. I think that's a very interesting thought, and that I might actually bring that up to people like Frank Donovan next time I have a chance to chat with him. That's a really good point. See, I learn stuff from you guys all the time. Isn't that great? I love it. Thank you for opening my mind. That would be important. Okay. Yes, with head spinning. Okay. Good. I'm sorry. I'm trying to go slow too. I don't want your head to spin. Please, I'm trying to take it slow on purpose. Very understandable answer. Good. Okay. About time people learned about the magnetic circuit and our connection with the sun. Yeah, and its magnetic field. Right. Yes, we do. Yes, and it's coming. It's coming, MJ Pierce. Space weather is becoming a bigger part of our world. And thank you SpaceX and Starlink. Thank you Starlink for falling out of the sky. No, I'm kidding. But yeah, I think we're going to be seeing more of that. And every time we see more of that, that means that things are going to become that much more. It's like raising awareness, through demonstration. Sadly, but it's true. So it will happen. I think over this next solar cycle, as we ramp up to solar maximum, I think space weather is going to be seen on the nightly news far more often, and it's going to be more correct than it's ever been. Right? Social media is really helping, and this community is really helping that as well. Would you say the magnetic field being all over the place is like a light bulb flickering dim, then very brightly? Being all over the place. More like wiggling. Here, how about this as an analogy? So here's our toroid, our magnetic field toroid, and it's just like a slinky, is very spongy and wiggly, right? I can squeeze it, I can bend it, I can pull it apart. If I pull it apart, these are magnetic field lines. The further apart they are, the weaker the field is. The more I compress them, the tighter, the stronger the field is. The magnetic field in the Earth system is very much like this, right? It bounces and wiggles and gets stretched and gets pulled out. So that kind of it's a force, right? Just like when you take magnets, your fridge magnets, and you push them together, and if they're oriented the same way, they're going to repel each other, and you feel it. You can feel it. It almost feels like you're pushing against a spring, right? As a matter of fact, people can talk about the magnetic field forces as a spring constant. So it's not, it shouldn't be that unintuitive to think about magnetic fields being things that actually have a force and a restoring force, and things that don't like to bend, and they don't like to move in certain ways, and so they'll repel or they'll attract, and that type of thing. That's what I'm talking about. All of that stuff causes wiggles in the magnetic field. So we're not talking about things being all over the place, like just chaos, but over a single spacecraft, you can have magnetic field wiggling back and forth, and that's going to look crazy to a spacecraft, to a single spacecraft. Now, if you have 4 or 5 spacecraft spread over a large distance, then something wiggling this much may look crazy for one spacecraft, but the other ones are going to see something a bit different. And so when you put the picture together, then you get a better idea, right? So it's perspective. That's what multi-spacecraft give you, is a perspective. But it's not just a matter of a bulb, like a light bulb dimming and getting brighter, because when you think about it from that perspective, that's just simply a value, right? That's just a number. That's just the strength of something. That's not a direction. I'm talking about the strength of something and a direction. Which way is it pointing, right? So instead of it being what we call a scalar value, we're talking a vector, something that has both strength or magnitude as well as a direction it's pointing. So imagine a magnetic field that is, that's sloshing, right? Moving around just a little bit. And it's sloshing. Sometimes it's a little bit tight, it's a little bit bigger, it's a little bit smaller, it's moving, it's tilted this way, it's tilted that way. It's obviously still structured, right? The Earth's magnetic system is. And I could probably play a movie at some point. If you still have this question later, I can play a movie. But I'm sure you've seen movies of the Earth's magnetic system, and how it reconnects and changes. I have movies in my M series that show this, how the Earth's magnetic system just kind of peels back and changes and stuff like that, but it still maintains a coherent structure, right? It's just dynamic. It's just a dynamic structure. Hopefully that answers that question, at least to some degree. But I mean, if it were just all over the place, totally all over the place, then these current systems couldn't survive, right? Which is actually one of the interesting things about when you talk about the Earth's magnetic system flipping, the dipole field flipping. All of this is controlled essentially by the dipole field, which is our strongest component of the magnetic field. When that reverses, all of this stuff will probably go away and totally reconfigure into something else for maybe a couple hundred years. And then it'll reform as the dipole field reforms. So it's going to be a very interesting space weather environment as the field flips. And I might eventually do a class on that. I got to find more research that's been done on the Earth's magnetic system as the dipole field flips. I would love to see how people want to, with an octopole field, for example, want to figure out how the current systems will go. And there may be some magnetic modeling on that, pushing particles through an octopole field. What would that look like? And see what types of stable current systems form. I guarantee you this, all of these indices, they probably won't work. They will no longer be isolated, right? Here we've created indices that purposely are isolating different current systems that we learned about, right? The ring current is essentially located at L of 4, right? L of 3 to 5, but mainly focused in L of 4. And we have an AE index or set of indices that are measuring things at just higher than L of 4, right? Just outside of L of 4. Well, we're isolating some of these outer current systems, like the region 1, region 2, right? We're isolating those current systems. We're not, we're showing kind of the tail current system a little bit, right? We're getting things that are mapping at high latitudes, which are further out, right? We're getting stuff that's mapping further out, right? We're isolating it from the heart of the Earth's magnetic system. So we're seeing where all the strong variations occur are up in these regions. You get rid of this dipole field and make it an octopole field where you have poles located, maybe 4 poles instead of 2. Now, you won't have just a north-south pole. You'll have 4 maybe mid-latitude poles. Your magnetic system gets totally reconfigured. L shells change dramatically, right? And they will map to totally different places on our globe geographically. And so this magnetometer chain won't make sense. It's not that we'll have to rip up the magnetometers and start over. No, we've got tons of magnetometers all over our globe. We'll just have to rearrange what indices we use. We'll have to say, well, no, now we're going to make a new index called the octopole current index or the octopole ring index or something. And there'll be 4 indices, and each of them will look at a different ring current for that particular pole. I don't know, something like that. Be crazy. Be absolutely crazy. When you have a multipolar Earth, just like you have a multipolar sun during solar maximum, you have a multipolar Earth, which we will see when our dipole field goes away. Wow, that's going to be fun. So we'll have to create all sorts of new indices for that period of time. Then, of course, we'll be able to go back to these old ones once a dipole field reconfigures. But for that interim period, we won't be making heads or tails of these old indices. We'll have to invent new ones, right? Not a problem. We'll do it. And it'll be a very interesting time to be alive, which none of us will see because it's not going to happen in our lifetimes. But maybe our great-great-grandchildren, right? Maybe they'll be living through it. Maybe they'll be the ones making those current systems or those indices. Okay, all right. Don't let me get too far off the beaten path here. Oh, good. I clarified it perfectly. That's great. Wonderful. Let's see. All right, let me defer. What I'm going to do, Craig, and a couple of the others. Let me defer some of the questions about our Earth's magnetic system shifting to some other configuration. Non-dipolar, non-current time. Kurtz, let me save that for the Q&A afterwards, okay? Because otherwise I'm going to get too far off the beaten path and everybody's going to fall asleep. But remember your questions. I will get back to them. And no, I'm not answering the question about micronovas. Go somewhere else. I mean, right now we're talking about current systems. That is so far off the topic. Okay, so hopefully that gives, talking about the AEs, the AE indices, gives you an idea that really we're doing our best here to exclude the ring current, okay? And this is so we can capture substorms, right? And we can be far more responsive to the little wiggles and not smooth out the little wiggles because we're waiting for something deeper in the heart of the Earth's magnetic system, the more protected part of the Earth's magnetic system. We don't have to wait for that to become disturbed, right? Which would smear out the little wiggles. We'd average them out. And then we wouldn't be able to be so responsive to all the stuff that's happening on the edge of the Earth's magnetic system. Okay. So here's what the AE, AL, AO, AU and indices look like coming from Kyoto. And the reason why I put up Kyoto is a fantastic resource. They do all sorts of different indices. AE is just one of them. But they're real time. And they're really good about how they're very transparent about how they show what's going on with these indices. So I know this isn't quite as recent as it used to be. I put this chart together back in 2020. So what you're looking at, okay, is the upper line here in this top panel. The upper line is the AU index. Okay, so it's the upper envelope of the auroral electrojet, right? Remember, we have an eastward and a westward electrojet. So that's the upper one. The bottom line is the lower index. So that's the lower end electrojet. I believe that lower one is the eastward and the upper one is the westward. I believe I got that right. Hopefully I didn't. If I've got that wrong, somebody let me know. And so what's nice about this, before we even talk about color, what's nice about this is that you can automatically already see what AE is, right? You subtract the two. That's this dynamic range. How big is this? See that? Isn't that nice? You can actually just right here, that's why I love the way Kyoto puts this together, is because it lets you automatically see very very quickly how disturbed the AL is, for example, the lower index is, and the lower electrojet is from the upper boundary. And then the other nice thing is that of all the 12 stations, that's what you see here, 1 to 12, okay, you can tell by the color how many of those stations have reported in. So sometimes you'll see early on when data is just beginning to be archived, if it's coming in real time, you'll see purple or blue. You'll see something where you've only had a few stations reporting in. And that means only a limited amount of stations in local time, right? Only a few. And you don't really want that. You want to be able, because the eastward and the westward electrojets, they have a tendency to, they encompass a full, the whole, what is the word I'm thinking of? All longitudes, right? So I'm sorry, my daughter's, I don't know if you guys can hear her, but I can hear her and it's very distracting. She's obviously very animated right now and talking to some people. So she's very loud. All right. Anyway, so just forgive me if I seem a little distracted. So when you only have, 4 or 5 of these different stations coming in, you may not have a really excellent picture of what AU and, what your indices are doing, right? So that's why I really do like this color code. So you can see here, for the most part, he's got, when you get to 12 or 11, 12, you're sitting there red, essentially, not magenta. Red is 11. You've got almost all your stations reporting where it's red. Where it's orange, you have almost all of them, 10 stations. Okay, so you really get to see that right away, whether you can kind of trust the data to not change, and that it's probably going to be what it is, or if it's just kind of a guess. And we've got some stations reporting, but things may be different, later on. So it gives you a kind of like a quality flag on the data. Isn't that nice? Which is super important when it comes to real-time data. That's one of the reasons why I love Kyoto. Okay, so that's the upper panel, and obviously you're looking at local time, or not local time, universal time. So it's the time of day, right? And really, kind of the rule of thumb here is variations, especially the dynamic range here. If you get that, if there's a difference of over 500, okay, in nanotesla, that can tell you when a substorm is. So, for example, see this substorm. That's a good example of a substorm. Again, substorm. Good example of a substorm. Then you get kind of quiet. Okay. And now down here at AE, the bottom panel, same kind of thing. This now, if you didn't like looking at the dynamic range here, this now will actually plot it for you. What is the difference between AU and AL? Well, here it is in AE. Okay. And now substorms really stick out. See that? That which kind of looked like it stuck out really sticks out. Okay. And again, really sticks out. And then down here, AO, this is the average, right, of AU and AL. And so that's being plotted here. Okay, which is not as important for you to look at, but it does tell you certain things when it comes to the overall strength of something, and possibly whether or not it's even going to go into become a geomagnetic storm. There's other subtleties about why people use AO. I don't know them, to be honest, because I've not done ionospheric studies. So I guarantee you there's a lot more richness in the differences between the AE and the AO index, and why you would use one over the other for specific studies of storms and substorms. Okay, but the nice thing about the AE suite, and that's what when I say AE now, I'm no longer just talking about this number AE. I'm talking about the suite of indices, because it's often referred to as the AE index with all four of them. What's nice about the AE index, the suite of indices here, is that you can very easily tell when you're going to have, at high latitudes, aurora, right? Because a substorm, oftentimes, anything over 500, okay. As a matter of fact, you're almost seeing, this is almost a geomagnetic storm, because you're seeing sustained numbers over 500. This is usually when you're going to be having aurora on the ground. Also, it's also a good indicator, the rule of thumb, it's a good indicator when you're going to have surface charging from auroral precipitation for spacecraft that are crossing through those zones. Okay, that are essentially in the post-midnight, pre-dawn sector. You're getting a lot of auroral precipitation, and you will get spacecraft charging. Okay, and sometimes internal charging. And this is for spacecraft not necessarily in geo. These are in space. These are for spacecraft not in geo that are crossing through the auroral zones. Okay. And I got that from Joe Fennell, straight from Joe Fennell, who's a very savvy physicist at aerospace. So believe it or not, aurora chasers are not the only people who can benefit from this. And radio amateurs who are using auroral propagation are not the only people who can benefit from the AE index. Satellite operators can too, believe it or not. So hopefully people, if you're worried about, and I'm not necessarily talking about Starlink, but I'm talking about people who have spacecraft that are in lower orbits than GEO. AE may not be a bad index to use for certain things, especially for spacecraft charging. Okay, because these are mainly electrons that are causing these that will be causing these types of wiggles. I should be careful, not causing, but that will manifest, that are likely precipitating during times of very disturbed magnetic field like this. Okay, another set of people who could probably benefit from this would be astronauts at the ISS, if they happen to be doing EVA or anything like that. You don't necessarily want to get caught in times where you're having substorms, because you can get what are called reps. You can get these very rapid energetic particle bursts that, if astronauts are actually dealing with, they're out in the EVA suits and they get these bursts. If they're going through the horns of the radiation belts, or they're going through the auroral zones, and they get some of these bursts, well, that gives them very high dose rate doses, basically, of radiation. And those are just beginning to be sussed out as a source of issue for astronauts on EVA. And a lot of these substorms, remember, these substorms are not during KP indices, big geomagnetic storms. So you may not even know that these things are happening, because they're not necessarily happening during solar wind, when the big solar wind storms, big CMEs or solar storms are coming and hitting Earth. They may be internal reconfigurations of the Earth's magnetic system. That's what substorms are. And so, in many cases. And so astronauts could be getting doses of things like this without any other index flaring up saying, hello, we've got problems. That's one of the nice things about the AE index, is that it can really be very sensitive to things. As you can see, even here's the next day, right? That was the 26th, here's the 27th. You can see things. We had essentially one substorm. It didn't last very long, so aurora would flare up for, an hour or so, and then quiet back down. And people really can use this. If you're at high latitudes, the AE index is where you need to go, because it really can tell you when you're going to get aurora. I've seen people literally, they could set their watch to this if you know what to do, if you know how to read it. And now, notice in this case, we start getting into a situation where the AE index goes over 500 and almost stays there, right? It goes up to 1,000, up past 1,000, and stays there for a long period of time. This is when you're going to start seeing other indices begin to light up, because now you're sustained disturbance. It's no longer just little bursts like what you saw here, like what you saw over here. Okay, this is sustained stuff. So as you can see very, very quickly, when you start getting sustained disturbances, things can get out of hand, and the AE index becomes less telling. I mean, it's very telling, but you get less detail. You don't quite understand what's going on, and you can imagine the system could get overwhelmed, and it can. Here's the next day. Once again, quiets down a little bit, so now you're back down to doing substorms, but lots of bursts. But it's kind of, I bet you wouldn't be surprised if this was active conditions to maybe G1 level on a KP index. So there's 3 examples of 3 different days during this particular storm, and I forget what the storm looks like later on, but I think I will have an example of that with one of the other indices. All right, any questions on the AE index? I guess I could put this back here for a sec before we go to DST. Earth just cracked. Cute. Let's see, what time is it? I got to see when I went. I'll probably do the DST index and then I'll stop. Okay. What if the magnetic shield is less than in the 90s? Wait, what if the magnetic shield is 90% less than in the 90s and the atmosphere levels are expanded and the ionosphere keeps getting opened in an increment of 500 miles by SpaceX? You're talking about as the Earth's magnetic system quiets down and Starlink is going to, we're not going to have to worry about that nearly like just worrying about a big geomagnetic storm. When a big geomagnetic storm happens, that's when the atmosphere is going to puff out quite a bit. And we shall see how well Elon's satellites stay in the sky. I think he's becoming quite aware that he could lose quite a few of them very, very quickly. Hopefully he's not being so cavalier as to think, well, I just launched them too low. Hopefully he's realizing that when people first told him to raise the perigee from, where he wants to sit, which is at 450 to 500 kilometers, that he really needs to be above 650 kilometers, that there was a real reason for that. I know he has reasons for keeping satellites down at 450 to 500, but I've been saying for years that they're going to fall out of the sky. And I'm not just saying that about the ones that he's launching at 210 kilometers just so that they can re-enter quickly. I'm saying that even the ones that are in active configuration and that they're well situated and at their parked orbit, during a big geomagnetic storm, he's going to lose quite a few of them. It's just going to happen. And it's going to happen over the course of a few days, because it's, when you get a big geomagnetic storm, it's not going to be just something that lasts for a few hours. This is going to be something that'll last for 24 to 48 hours, and then, possibly 72. And then things will then have to slowly, actually what ends up happening is that the atmosphere probably inflates a bit more and there's a delay, and then things will slowly calm down. So satellites that are in 400 kilometers, 450 kilometers, they're going to deorbit quite quickly. And if he's got a whole slew of them, that could be a problem, be a real problem. So that's what I think that is what he's going to face first. And I think he'll correct, the SpaceX will correct the errors in judgment. And likely their orbit parameters will fluctuate, will be cyclic along with the solar cycle. And they'll learn to be a bit more conservative during solar maximum and can take higher risks during solar minimum. That's just going to be the nature of things. Space weather is going to factor in far more in the CONOPS of these satellites, these constellations, these big constellations, than they ever have before. That's just a fact. It's just going to happen. Shame he uses the name Tesla. Oh, well. Anyway. Okay. Let's see. Okay, good. Yeah, thanks, Jerry. Appreciate that. Keep comments relevant to the topic. So good. I'm glad, it sounds like everybody's okay with that. So I'm going to move to the DST index, and then I'll take questions about DST, and then we'll calm down, save the rest for next time. So as you might imagine, the DST index is no longer going to be something that's super high, right? We talked about, with the AE index being at L of 5 and above, right? Now we're obviously not getting into, we're a lot lower than this, right? We're now in L shell of 4 and 3, right? As you can see, we've got the equator sitting in here. The magnetic equator is somewhere in here. So we're dipping down into L shells as low as maybe almost 2 to 3, and up into L shells as high as maybe 4, but definitely under L shells of 5, right? So now what we're doing is that we're taking all those high latitude variations, and excluding them, because we don't want magnetometers that are going to be sensitive to that stuff, right? Because now what we're wanting to measure is the current system that is here, right? We're going to try to measure inside of all this extraneous stuff out here, out in here, and over here. We don't want any of that stuff anymore. We want stuff that's more in the heart of the Earth's magnetic. We could figure out how many in the heart of the Earth's magnetic system. So that's the ring current. Okay, and the reason why the ring current is super important to isolate is because now, when we get a big geomagnetic storm, speaking of big geomagnetic storms, really it's the ring current that gets energized. Okay, granted, the radiation belts get energized too, but the radiation belts, especially the outer zone, is co-located with the ring current. It just doesn't have the mass that the ring current has. The ring current has so many more particles. And so the ring current really is containing the current, the energy of the system. It is considered the storage ring of the Earth's magnetic system. And it is so strong that when it gets energized by having solar storms slamming into here, reconnecting with the Earth's magnetic shield, folding the flux back and dumping the particles in the tail, and all that stuff gets filtered back up here, and now and a lot of it gets trapped. You're trapping stuff in the ring current. Okay, you're trapping particles in this system that then slowly get energized, right? But the more stuff you dump in here, right, the more you're going to have this tokamak effect, because you've got a magnetic slinky, which is in the shape of a tokamak, and it's a particle accelerator, right? So you're going to be creating more current, but that has to happen over time. That's not something that can happen with just a few wiggles out here and then stop, and then a few wiggles out here and then stop. No, this has got to be a constant slamming in of the Earth's, slamming in of the Earth's magnetic system, folding the flux back, and constantly mass loading, what we call mass loading the tail. That's what scientists call it. You mass load the tail. You get dipolarization, things change. Some stuff gets shot that way, but a lot of stuff gets shot in to the Earth system. You're loading it, okay? As that continues to load, this current gets energized. As this current gets energized, it creates and induces a magnetic field. That induction of the magnetic field is in the opposite direction of the Earth's actual magnetic field, and it reduces the strength of it. Okay, we measure that on the ground using DST, using these magnetometer stations. Okay, only 4 of them, right? Just low latitude. Spread out in local time, smartly, right? Because we want to measure it all the way around, but all kept to reasonably low L shell to exclude all this stuff up here, all the high latitude stuff. Okay, so it's a 1-hour interval. Okay, and we'll talk about the positives and negatives of a 1-hour interval. It's been available since 1957. So lots of historical stuff. That's part of the reason why you don't change it. When you have something that's been around for a very long time, you don't want to change how you do it, because then you can't compare historical, events with current day events. So there is something to do with, with not just repeatability, but sustainability over time. Again, we're measuring the horizontal component, right? And the H component, why it's so important. And let's see, what do I want to talk about in here? Oh, there's details of the protocol of how you compute it. I'm not going to go into the details. You guys can read this. I'll let you sit there and read that if you really care to. But as you can see, it's not completely trivial, right? Not only do you have to deal with subtracting out all the variations, the quiet field variations, but you also have to then normalize it to the equator, to the dipole equator. You have to worry about, not just the geographic equator, but the magnetic field system, because the dipole, the ring current is not aligned along the geographic equator. It's tilted, right? It's tilted with respect to the Earth's magnetic system. I mean, to the Earth's geographic system, because it's actually going east-west according to the dipole field, or to the Earth's magnetic dipole field. So you have to worry about it being normalized to the dipole equator. Okay. Yeah. So they're talking about, even these guys tonight, they talk about Kyoto. How cute. I didn't realize that. So let's take a look at the system, right? Obviously, again, I keep pointing to the purple current, right? Inside of the high L shells, which makes sense. So that when we look at this diagram, now we're looking at stuff that is, we're talking about stuff when, let's see if I can get where we are here. My goodness, we have, look at SJG. I mean, we're talking about L of 1,5, right? That's located in here. Follow this L shell, it's L of 1,5, right? So we're talking stuff that really is impinging upon the plasmasphere. Okay, that's how inside we are. Okay, we're really low. But you can see it's going from, definitely excluding anything from essentially L of 3 and higher, right? And that's definitely, so it's to some degree, when we talk about the ring current being focused at L of 4, we're almost excluding the bulk of it, probably so that we can isolate away from the high latitude stuff and some of the coupling that we see in our upper atmosphere, right? Because I remember I talked about how the atmosphere can really make things difficult. And what else makes things difficult? The tail current on the night side, right? So when we have, and because, the Earth is rotating, so all of these will rotate, these stations will rotate through the Earth's night side, period, right? So they all will have a component that comes from the tail current. So the further in we can go, the lower L shell we can get, the more we exclude any of that stuff. So here are the stations that contribute to it that are active right now. And you'll notice some of the stations are also for ASY, which is another index that measures the ring current. Can you talk about SIM? Okay, no. Now, before I go into the DST and look at the DST current system or the DST index, what I want to make sure I let you know is when we look at DST and the way it's been historically calculated, granted, when we looked at AE index, we saw that it originally started as a 1-hour index. AE reasonably, quickly shifted to something at a much higher time resolution. And it's painfully obvious why. I mean, look how fast the deviations are in the DST, in the AE index, right? Things change over very short time scales. A 1-hour average would quickly smooth out a lot of the variability that you see in AE. DST wasn't quite like that. Because DST deals with, the heart of the Earth's magnetic system, because it takes a long time to mass load the Earth's magnetic system over time and build up that ring current, you had more time to respond. Right? So DST didn't really suffer like AE index did for not having high resolution until recently, where we started getting more scientists saying, well, why are we doing it this way? We need higher resolution than 1 minute. We're looking at, because we're beginning to get better, especially with the advent of spacecraft missions. We actually do need higher resolution to resolve things that are going on in the Earth's magnetic system that are, that then can be correlated to things on the ground. But if we're stuck with a 1-hour system, because historically that's what we've had, well, then we're stuck. Enter things like SIMH, enter things like ASY. Okay, these are current system. These are alternatives to DST that are oftentimes interchangeable. Now, are the stations exactly the same? No. Are they oftentimes very similar? Yes. For example, right? 3 of these stations are used for ASY as well. Do I know all the details of the SIMH? Obviously, H is the horizontal component, the symmetric horizontal component. Do I know all the details of these alternative DST indices? No, I don't. Why? I'm not a magnetospheric physicist, but I want to let you know that they're out there so that you can get higher resolution data for essentially for DST and a DST equivalent. Are there differences? Yes. But for the most part, they're minor. And so I'm pointing you to this particular article. It's one of several, but I like this article because they talk specifically about doing a comparison between DST and the SIMH index during not just big storms, but also small storms as well. And so they found that basically the two agree with one another. If the storm isn't too large, if the storm is less, if the deviation, the index is less, sorry, I have to be careful, is greater than, because we're talking about a negative number. We'll talk about why it's a negative in a second. But if we talk about the number being for a storm being higher than, greater than minus 300. So in other words, minus 300 or minus 250 or minus 100, something closer to 0. If the storm is a smaller storm, which causes a greater deviation, sad, isn't it? Because of that negative number. As long as the storm is a smaller storm than something that is minus 300 nanotesla, then the deviations between DST and SIMH are really not that bad, about 10 to 20 nanotesla. When you get into stronger storms, then it becomes a bit of a problem. So for most storms, so we're talking about, for those of you who are familiar with KP, storms that are around KP of 6, maybe 7, you're good. Get into 8 and 9, that'd be a real problem. You don't necessarily want to be looking at that if you really want to do studies with DST. So there are variations, okay? And similar arguments can be said for the ASY index, but all the details are kind of lost. So I still use DST to a great degree, once again, mainly because of Kyoto and because of historical reasons. But I do lament sometimes that we don't have better time resolution for DST. So here's that same storm, 26th through the 28th of September that we looked at for AE index, right? Remember? The AE index, it was pretty wiggly. Well, here it is for Kyoto for DST. What do you see? Do you see much? Not too much, do you? Granted, this is a horrible scale because, this is an auto scale for Kyoto for DST. But as you can see, DST typically over this entire month in this case really doesn't wiggle that much for quiet time, right? You can get down to very small storms, minus 50 nanotesla, right? And here we go into this storm period where you've had multiple kind of stuff going over the course of maybe 4 or 5 days, but you're not seeing a lot of detail here, okay? Notice almost everything in DST is negative. Why is that? We're measuring the ring current, okay? In the ring current, what you're measuring with a westward current is it induces a negative magnetic field. It's depressing the magnetic field of Earth, therefore negative, okay? So you're getting a depression of the Earth's magnetic system, depression of the Earth's magnetic field. So DST variations are going to go negative when there's a storm. Here's sim H for the same period. A little bit more detail starting around. So here you see a little bit of wiggles, right? But things are kind of smeared out. And granted, I should expand the scale, but I just didn't. I just took a plot instead of replotting it myself. But here you can see, yeah, it does pop up a little bit. That's typical when you get a compression. The Earth's magnetic system, gets compressed and the field goes up. DST will actually, in that sense, DST, well, it goes positive. And then as you begin to go down, you can see here's a big, gosh, I'm at a loss of words. I'm sorry. My daughter is just screaming and laughing. Very distracting. I don't know if you guys can hear it, but it's very loud from my point of view. So I am quite distracted right now. Anyway, so here's a jump down from obviously something slamming into Earth and actually having a decent, storm response. And so you get what ends up being, in this case, a main phase of a storm. It doesn't last all that long. But it looks like it's down to easily 50 to 75 nanotesla, if I can tell from the tick marks there. But you can see a lot more detail, right, because of higher resolution. So you can see it at a 1 minute resolution is much better. But essentially the same level of deviation for these small storms, right? But from this perspective, if you had to think about the AE index or the DST index for this level of storm, which would you rather look at, right? Which do you think gives you more information? This or that AE index that showed you even all the little substorms that were occurring? Yeah, probably AE, right? So let me go back for a sec. Let me see if I might have them side by side, because I do the same thing with KP, but I don't think we have time to go through KP today. Do I show AE? Yeah, you know what? I'll just show it for a second. Maybe I will. Hold on. Is that the right storm? I don't think it is. I think I have to show a different storm. It's October. No, that's 2003. It's a 2017. Yeah, I don't have it for the storm. Strangely enough, I start going into the. I did the KP. Isn't that funny? I didn't do all side by side. But I do the KP for that. That's too bad. Whoops, that's not what I meant. I meant to do this. I'll make that chart for next time. I'll be sure to add that in. Because what I wanted to do was have a side by side between the KP and the AE index and the DST index for this storm. But I didn't have it. I'm going to make sure I do that next time. So again, here's that same storm here for the KP index, the AE index. And you can see it's just so much more telling, isn't it? Right? You can see exactly where the substorms are. This kind of stuff won't even register necessarily, or at least not very well on KP, on DST. Where it starts registering really is around the 27th, where you really start seeing it going down. And because you can see it here, it was sustained, right? You had not just a few wiggles and bumps, but it was sustained. So if I go, well, I guess you do see a little bit of something, at least in SIM on the 26th, but then it's the 27th is where you really see it sustained. Same thing here. 26, you see a little bit of something, but then it really starts going down and staying sustained. Now, in a big storm, you'd see DST go way down and then slowly come back up in what we call the recovery phase. And we'll talk about that next time when I go into the bigger storms. But for little storms like this, you're going to just see so much more detail in what's going on. You would never try to tell aurora is happening from this plot or even this one. It's just not, there's just not enough detail there. But in AE index, you definitely would. So, and with that, my goodness, I was hoping to get to KP today, but it doesn't look like I did. We still got quite a bit to go. So I will pause here and open it up for questions, guys. But at least I was able to get through high latitude stuff. We did a nice review. Got through the high latitude stuff where you got to see, the quiet variations, how those are subtracted out, and then you got to see both high latitude index compared to a low latitude index and how they differ, right? Because there's going to be reasons why you might want to look at one compared to the other. And we'll get a much better feel for that. We'll even compare with a mid-latitude index next time so that you'll see how you get a little bit of each in the mix when you look at KP and why that ends up being useful in a global sense, right? And why that became kind of the standard index to go to for, let's say, the Space Weather Prediction Center. And sadly, it became adopted around the entire world for your go-to space weather index for non-experts, and that it serves certain communities, but it doesn't serve certain communities, and so it becomes very confused as to why in what instances does KP work and what instances does KP not. But we'll talk more about that next time in the very next course that we do. Okay. So questions. Hopefully this was useful. I hope, even though we're only partway through it. I know we had a lot of review in this one, but oh, good. I'm so glad. Tim, you say you can't hear my daughter at all? Yeah, she's screaming in the other room. I have no idea. She's playing Xbox and just really animated. So I can hear her sometimes, but it's very faint. Okay, good. It's Mother's Day. Yeah, right. Of course it is. So I get to go out and tell her and say, thanks for the Mother's Day gift. It's now immortalized on YouTube that you were screaming in the background and I couldn't teach my class. Oh, that's funny. Okay. Okay, let's see. Good. I'm so glad. You guys, you didn't get distracted as nearly like I did from my daughter. Hopefully everything was clear. Was this a good class today? Did this start whetting your appetite for understanding space weather indices much better than you used to? And hopefully getting you to understand that there really is a method to the madness of all the different indices that we see on the ground. And you really can, depending upon what it is you're looking for and where in the Earth's magnetic system that you are focusing on knowing where the disturbances are, you actually can on the ground begin to isolate these things and include what you need and exclude everything else. Now, granted, from that review I showed you, there's a lot of dynamics, right? It's not perfect. So oftentimes we have to exclude more than we want. If we really want to keep stuff out, we have to really be careful and only have a tiny bit in there. But that tiny bit is enough to get us, like with the ring current, we're really low in our L shell and what we're encapsulating. But in order to exclude all of those other aspects that distract us from just what the ring current is doing. But it's important, because it actually does allow us to really only focus in on the things that we need. I'm seeing stuff go by really, really fast now. So I'm like, oh my goodness, what am I missing? Let's see. the field has more effect because it's like hitting a magnetic spinning top on its side with a nail and gently pushing it. What is this? I missed something. I've missed something from you, Furious TV. Sorry, sad to say. I'm only catching the bottom part of your comment, so I apologize. Things just scrolled too quickly. Oh, just came off the NSF stream. Yeah, I've noticed a lot of people just finished joining. Hopefully you guys can catch the rerun. Yeah, thanks for joining me on Mother's Day, by the way. Oh, good. Secret Owl, Aaron, absolutely, yes. Great class, very useful. Thank you, guys. Wonderful. I'm so pleased that this made sense to you and it helped. I'm so pleased to see that. That's just great. You said, is it an engulfing storm that overloads the magnetic shield because it is more uniform than a lower type of ejection? You mean a smaller type of injection that provokes a? It's no, it's not engulfing. It's what you're dealing with are things like reconnection rates. First of all, you have to have something that's going to have the right magnetic configuration to consistently reconnect with the Earth's magnetic system. Then you're dealing with rates. You're dealing with like dynamic pressure. How fast can you inject stuff into the Earth's system? And when you inject stuff into the Earth's system, how strongly can you inject it? So you're dealing, in that case, you're dealing with something in the solar wind that has strong magnetic field that can pull flux back and open the Earth's magnetic system up very, very quickly. Because as you reconnect flux, you have to, if you have a strong magnetic field in the solar wind that's going to reconnect with the Earth's magnetic shield, well, if it's a strong magnetic field, it can pull back a lot of flux really fast and reconnect very, very quickly and over a wide, not just area, but a depth, penetrate quite deeply, because it's peeling back flux as fast as the Earth's magnetic system can shove it out there. And so it just peels it back so rapidly. As a matter of fact, when we looked at really strong events, models, for instance, of the Carrington event, the day side, what we call the day side magnetic flux, gets peeled back almost completely. I mean, I would love to have known what happened to the ring current at all during that period, because to me it looks like the Earth's magnetic system got so peeled back so far that there was nothing that was trapped. All the particles got broken. The jailbreak happened clear into the ring current, so it just basically flushed all of those particles out. It was just looking at the models, it was unbelievable how far in the solar wind made it. To up to almost look like the edge of our plasmasphere. It was pretty crazy. And so that is a function of not just the dynamic pressure from the intensity, and speed with which that solar storm hits Earth and is just slamming into the Earth, but it's also a function of the magnetic field being able to peel back so much flux and mass load the Earth's magnetic tail so quickly. That is what causes these really strong geomagnetic storms. It's not an engulfing, from the perspective of the size or something of it. It really has everything to do with dynamic pressure, right? How dense something is, how fast it's moving in, and how strong the magnetic field is. If it's and it has to be magnetic field in the right direction, and that right direction is basically a southward field with, and possibly a strong east or westward directed field, because you can couple very strongly in that way as well. It's harder to couple if the magnetic field is pointed northward, at least in our current configuration. It can happen, and I talked about that in what class was that? Was that an M class or an I class? I can't remember. I think it was one of the early I classes. I think I was talking about it because we were talking about the convection of the Earth, of the magnetic foot points, and how they change depending upon the type of reconnection, whether you're getting southward magnetic field reconnection or northward pointing, because that changes how the solar wind magnetic field couples into the Earth system. So yeah, so hopefully that's a long-winded answer to your question. Okay, thank you for Julian. So you say thank you for those entry points on magnetism knowledge as usual. Excellent, Julie. I'm so glad. I'm glad that you're learning. I'm glad I'm able to teach you. It's not easy. Whoops, and I'm missing another one. Hitting a magnetic spinning top on the side with a nail, then gently pushing it uniformly. Oh, that was the second part of your question. Hopefully I answered that all right. Eric, thank you. It was worth it. I'm so glad. Frederick says, you have so much knowledge. Amazing. My brain can't handle this much. I'm sorry. I can't either. I make lots of mistakes. So, I'm just an aurora chaser wanting to learn more how to predict aurora. AE index, AE index, AE index. And when the AE index gets overwhelmed, the aurora is probably south of you, depending upon where you are. The more I learn, the more I realize that I don't know much at all. Exactly. That's the danger when there are people out there who try to who take these YouTube courses and then they think that they're an expert and that they can teach this stuff. It's like, oh my goodness, I'm an expert and I can hardly teach this stuff. I mean, there's definitely areas where I fall very short, and I am so grateful that I'm a card-carrying member of the scientific community, because they are not shy. My colleagues, when I do something wrong, they come back and hammer me and tell me, Tamitha, that was just flat out wrong, or you forgot this, or why did you use that word? That's a horrible thing to say. And so, I am held accountable, and I honestly, I wish more scientists would come and hold me accountable in a nice way, please. But you just have to have so many different PhDs in so many areas to get it all right. And I have, to this day, I don't know a single scientist who can get it all right. So, all I can say is I'm in good company, because there's so many brilliant people doing so much brilliant work, and it just, the complexities just keep coming. So, please forgive me my failings, but definitely please don't think that me teaching you this stuff, don't feel badly if you have a hard time absorbing it all. And that's one thing, because it is that complicated. And B, if you don't have a hard time absorbing it all, don't suddenly think that you have a PhD level understanding simply because I've taught a few YouTube classes. This is really just scraping the surface. I mean, I don't mean to scare the people who are already overwhelmed, but it's true. There's so much more depth. I mean, and we're just talking about the conceptual side of things. Imagine adding the physical mechanisms along with it. It becomes overwhelming very quickly, right? So, okay. So it's great. You're glad you asked. Oh, good, Fears. I'm glad that ended up being a good question, or a good answer for you. That's wonderful. I'm better user of space weather reports because of your work. Oh, you're very welcome. KD8TTE. Thank you. That's Matthew. Thank you so much, Matthew. That's the whole point of all this, is to try to allow you to make the most of the information that you have, and it helps you better internalize, these reports, and be able to benefit from space weather reporting. That's exactly what we want to try to do. Right on. The hard part about everything is everything about knowledge, how to make something complex easy to understand and digest. Yeah, and I still work at that. I'm not as good as I should be, but yes, I'm trying. Sky thing, you are so humble. Oh, yes, that's right. Every scientist makes mistakes or they don't learn. Yes, and I make plenty. So thank you. I appreciate that. I am the first person, and I've mentioned this before, I'm the first person to say I don't know. When I don't know something, I really will say that. I won't try to make up an answer. Or I'll say, this is my best answer, and that it's speculation. I try to be really honest about that, because I just know that it's just impossible to know all this stuff. There's just too much. Okay, great. Nice to have an overview, and we can dig into the details, right? And hopefully I give you enough information where you can dig into the details. Potsdam is a great place. So is GDF. We'll be talking about that next time, when we get into the Bartels diagrams, or GFZ rather. When we get into the Bartels diagrams, I'll talk about this website, so you guys can get a better feel for it. And there are other places to go as well. So, so anything else? I'm going to check. Let me check really fast. It looks like I've got everything. There's a few more. Okay. Space weather plus radio astronomy with a side of ham radio. Yeah, and aurora. Right. Yeah, that's about right. As I try to get it on the side of things where you have where the information that I give you is very usable in the trenches, right? It's not from an academic perspective at all. So that's one nice thing, is that I will definitely give you information that hopefully you can hit the ground running with and use. So let me check really fast for Patreon to see if anybody has asked me questions on Patreon. I appreciate you guys spending your Mother's Day with me. Joe says, Happy Mother's Day. That's so sweet. Thank you, Joe, WC4R. Lisa said, Happy Mother's Day. That was very kind. Oh, and Deepak, so good to see you. And Space Girl Heidi. Oh, no, I hope. Okay. I wrote them down and I'm all ready for class. Space Girl Heidi, I never saw any of your questions, so I hope you got them all answered. If not, you know what to do. Just ping me on Patreon, either in the comment section on Patreon, or ping me, via direct messages. As a matter of fact, I think I have a couple direct messages. I should check. Looks like only one. So good. Good. I think I've answered a lot of questions. I can tell I've done a lot, guys, because my voice is getting hoarse. Oh, that's strange. I think Heidi wasn't able to make it. I don't know why. It's strange. I don't know why she's not able to make it. All right, well, I'll chat with her later. Good, Greg. You understood every word. I'm so pleased. That warms my heart. I'm so happy. Put the Potsdam link back up. Where are you? Sorry, I had it up for a second. There you go. Above me. I don't want to give away some of the fun stuff when we talk about the Bartel's music diagram. I'll save that for next time, because that's such a fun thing. You guys will be super impressed by what you're able to do. How you can impress your friends when saying, "Hey, I can read KP in a way you've probably never seen." But I'll save that for next time. You didn't get scared off, just interested. That's good to hear, Frederick. So glad for that. Okay. Oh, Andy. Hi, Andy. Good to see you. U.S. has Mother's Day early. That's right. Europe and Canada, I think you guys have Mother's Day in a little bit. But yeah, we have it right. We have it today. Yes. And hi, Spirit. Happy Mother's Day and many blessings. Yes. Thank you so much. I appreciate it. I'm going to go spend the rest of my day with my family. Will Mercury and or Venus between Sun and Earth divert? Oh, goodness. Yeah, you're welcome. Many thanks. Right now we're just focusing on Earth, so I'm not going to go into planetary stuff. You guys, Patreon members will have to tell me if they want me to do any space weather at other planets. That would be a very interesting topic. Mars has some very interesting space weather, for example. So does Jupiter. Oh my goodness, Jupiter's kind of scary. It's because its moons really affect its space weather. It's a crazy place. Okay, Pat, you make the information easy to understand. Oh, thank you so much. And practicable real world uses. Very cool, guys. Okay. Oh, is there, again, Frederick? Okay, so for the timeline, this is a perfect one to pretty much end with. Was there a timeline direction order that we should do the YouTube classes? Yes, the order of the YouTube classes, I guess I might be able to do this here. Hold on a sec. I might be able to, if I go to YouTube really fast, I will try to pull my channel up. Maybe it's up. Oh, good. Okay. So if you go, and I apologize for not having, let's see. I apologize for not having my iClasses up yet. But if you go to the classes, oh, good, you can't see it. Okay. If you go to the classes, you guys can see I've got the C course series. See that? I've got the F course series. I've got the P course series, W, H, and then M. And that maybe the only thing I have, because I need to organize the I's, and I'll do that next. But C stands for coronal mass ejection. F is for solar flare. P is for particles, so radiation storms. W is for solar wind. H is for heliosphere. M is for magnetic shield, magnetosphere. The reason why I use the letters that I've used is I've explained them already. I'm trying to stay away from the G, S, and B and R scales that NOAA uses. So you won't see me use any of those letters because I don't want to get people confused by it. Okay. But right now they look like, if I get it right, they actually look like they're in order. So in other words, you'd start with the C series, and then you go to the F, and then you go to the P, W, H, M, and then there's the I series, meaning ionosphere, which I have yet to organize, but the I series is done. We are now starting the E series, meaning Earth. I can't use the word ground because G is a NOAA scale, G for geomagnetic storm, so I don't want to use G. So my Earth, my ground-based series, which is what we're starting, is now called the E series for Earth. Okay, you know, if you have a better acronym or better letter for me to use, I'll use it. So if you click on one of these, whoops, no, stop. How do I kill this? Okay, how do I get to the view full playlist? Okay, there we go. So if you view the full playlist for, let's say, the C course series, okay, you're looking at it here. There's only 3 courses in here, and it looks like, my goodness, boy, did I do these a long time ago. I wasn't even on my green screen yet doing my courses. I was still using my television. How funny. But the C course series, so you can see here, it talks about what it is, and then it says down here in the description, it says this is the first series in a set of courses on space weather basics. Okay, learn about the largest source of space weather in an easy to understand language, blah, 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 blah. Okay, prerequisites, none. See that? So in my series, in all of my course series, okay, and I have it listed in order, and it'll say part 1, part 2, part 3, or it'll say C1, C2, C3. So there's 3 courses in the chronal mass ejection series. If I go back, and now I'll do the full playlist for the solar flare course series. Once again, in this case, now I have 4 courses. Oh, and I start using my green screen. How cute. Okay, so in my flare course series, there are 4 of them, F1, F2, F3, F4. And if you look at the full description, okay, I talk about what it's about, and I say prerequisites. Prerequisites, course C1, C2, and C3. Okay, so I have that all listed for you. And if we keep going to each of the series, you'll see that before too long, I'll go ahead and I'll go to the M course series. Let's do a full playlist for the M course series. Okay, you'll realize this is an advanced course. Whoops, what is that? Oh, sorry. This is an advanced course, right, that talks about all of this stuff. Prerequisites, all courses in the C, F, P, W, and H course series. So you can see, unless you know everything about the first chef, you do not want to take the M courses, because these M courses are the first set of courses in the second chef series. You really need everything in the first chef series in order to understand the second chef, right? Just like now, we're doing everything on the ground, and in order to understand the stuff I'm talking about now, as we're working on the courses at the ground level, you need to understand everything in the M and the I series. Okay, well, that's, so hopefully that clarifies those questions about my classes. Okay, and you can see here's M1, M2, M3. Okay, does that make things clear? And like I said, I will put this breakdown on my website. I do have plans to do that. Until then, you kind of have to shuffle through the descriptions in the course series on YouTube, but you will find them. The only thing is, if you're looking for the I series, I have yet to put that. They're there. They're just not organized on a playlist yet, because I'm a one-woman show, so I got to do that on my own. So, secret we don't have mothers, lucky humans. That's great. You guys are funny. Okay, anyway, so hopefully that answers that question for you, Frederick, and anyone else who's curious about it. I know Space Girl Heidi was looking for that too. So hopefully this will help keep everybody on their toes regarding all that. And like I said, I'll get the iCourse series set up here soon. I tell her thank you, but if I were your daughter, I'd tell her you're a jerk for talking smack about her authenticity on Mother's Day of all days. Well, considering, and I'll laugh at that, because considering she's that loud all the time, and even when I tell her to be quiet because I'm recording or I'm doing something live, She doesn't. And she's only 12 and she laughs at this. It's not a problem. My daughter and I have a very good relationship, so don't worry, Karen. You don't have to be too strict about that. That's an interesting take, but it's I definitely wish you could see the actual dynamic my daughter and I have. I think you change your mind. All right, so I think that's it, guys. Um, and thanks, Jerry, both you and Mike Richardson. Thank you so much for being a moderator over Mother's Day and staying with me for a few hours so I could teach this course today. You guys are just fantastic and my heroes. There's no doubt. Okay, so I think this is good. Sounds like I answered everybody's questions. And guys, have a great Mother's Day, and enjoy your weekend.